Check 1, 2. Okay. Good. All right, good morning, everyone. We'll be underway in just a moment, but a couple of quick announcements. First of all, if you are a speaker from yesterday, we're trying to locate your content to get that posted online. So if you can grab one of the papers chairs during one of the breaks to make that handoff, we'd appreciate it. And then for speakers today and tomorrow, the same applies, right? Please get with your session chair or one of the papers chairs so that we can get your slides posted to the website. Appreciate that. Just a quick note about the banquet, right? So again, great response from you guys with attendance, but we are oversold, and several of you have already let us know that you have alternative plans or things of that nature. So again, appreciate that. Thank you for keeping us in the loop. We do have a few folks that are still waitlisted, and so during the first coffee break and poster session, if you will go to the reception area, you can pick up your ticket, and they will be handed out in priority order based on date and time of registration. Likewise, if again you're not attending and you haven't spoken with us already, please do check in and let us know. That'll free up a spot for those folks who might be on the wait list. So please take care of that during the first coffee break. And again, any tickets that have been unclaimed at that point will move to the folks on the wait list. And again, just to review, we'll have more details later in the day about how to make it down to the harbor for boarding the boat. But their ticket will have a group number on it, and that will determine your departure time. So please be aware of that. One other note, tomorrow we will be distributing the best paper ballots in the morning. And keep that in mind as you're watching the presentations and reading up on the papers. Those will be handed out tomorrow, collected after the last paper session. We will, of course, tally the votes and then present the best paper award during our closing remarks on Wednesday late morning. Let's see, last note before we get underway for the day. There's been a suggestion to grab a conference photo. And back in the days of the Interactive Ray Tracing Symposium, which was much smaller, that was relatively easy. We're going to try to organize that, weather dependent, outside, perhaps looking down from the deck into the parking area where we can all gather, or maybe right here in the lecture hall if the weather isn't agreeable. So again, stay tuned for more on that, but it might be a neat opportunity to gather together and try to get a group photo. I think that's it as far as announcements go. So without further ado, we will hand it over to Dieter, who will chair the first session. Thank you.
Thank you. So good morning, everybody. This is a special session. You might have noted that it's split into two sub-sessions of 2 papers each. So we'll start with the topic on perception and in motion, encompassing 2 papers. And our first presentation is going to be entitled, CG-VQM plus D, Computer Graphics Video Quality Metric and Dataset. I guess this is a trend in metrics to have long acronyms. So this is work from folks at Intel. Our presenter is going to be Ashkai Jindal, and his co-authors are Nabil Sadaka, Manu Matthew Thomas, Anton Keplanian, and Anton Sochenchov. Thank you.
Thank you, Dieter. Let's dive right in. So let's start with why do we care about visual quality? I'm pretty sure every single graphics practitioner in this room at some point in their projects had come across a situation where they had to trade off between performance and quality. It could be situations like rendering your optimizer. Let's say there's a limit on number of pixels you can shade. So you have to find out which pixels to shade and which not to, so that your visual quality remains pristine. Or it could be a situation where you are streaming your games over internet, and due to various circumstances like changing server loads or changing bandwidth, you might have to throw away some data packets. Now the question is which data packets to throw away. Again, to retain the visual quality. And more recently, it's becoming a trend that more and more pixels are just AI generated and not rendered. And in those situations, it's super important to ensure that the hallucinated pixels match the targeted intended quality. Visual quality has become the currency you spend to gain speed, compression, or power savings. And sometimes you overpay, sometimes you underspend. A good metric helps you budget wisely. So now that we have established that visual quality is important, how do we quantify it? How do we measure it? The golden standard is to just have a human look at the video. You will get exactly how you will perceive your rendering technology. But of course, this is not scalable. It's expensive. Human time is expensive. Humans are slow, and it's very hard to recreate their responses across different lab conditions. A very common alternative to user studies is image quality metrics. And yesterday, we saw a lot of PSNR and SSIM scores in different talks. And this beauty to that, it's very simple, it's computationally efficient, and it's reproducible. But they suffer from an obvious problem that they don't model temporal artifacts. Let's see if this artifact is visible here. So the first two images look almost identical. They only differ slightly in terms of brightness. And image quality metrics would say there's no error between the two images because they are slightly different. But when the same two images are played consecutively in a video, suddenly the error becomes visible as annoying flicker. It's not super visible due to the projector washing it out, but take my word for it. OK, so we need to model temporal artifacts. There are video quality metrics for this purpose. Some common examples are VMAF, STIRRED, or all sorts of video visible difference predictors. And they do model temporal artifacts. But they have one major problem. All of them were designed for streaming use cases, for example, Netflix VMAF or color video VDP. And they are designed for natural content and compression artifacts, which can be very different from graphics artifacts. All the modern rendering techniques leads to artifacts which are very different in statistics than compression artifacts. For example, neural upscalers can lead to ghosting if the motion is not tracked very well. And path tracing methods can lead to shimmering and high-frequency noise. Aliasing and flicker, I'm sure everyone's quite familiar with them. And more recently, you get weird sorts of hallucinations in view synthesis methods, and it's hard to even describe them with words like aliasing or flicker. These artifacts are spatial and temporal in nature, and they do not resemble compression artifacts, which are blocky kind of in nature. And existing metrics are not tuned for these artifacts, so naturally they do not work very well for computer graphics distortions. A sentiment that is kind of resonated in this room. So there's clearly a gap. There is no data set with realistic rendering artifacts and human ratings on those artifacts. And there is no metric that has been tuned for real-time rendering distortions. So we introduced two key contributions. One is a dataset, CG-VQD. It contains rendering-specific distortions and their human ratings for a wide variety of scenes and rendering techniques. And a CGVQM, it's a full reference video quality metric based on pre-trained 3D CNNs. And it is seen to perform in the next few slides that it works really well for graphics datasets and traditional datasets too. Let's dive into the dataset first. Like I described earlier, existing datasets like from the live group or VCAG group, again, focus mostly on natural scenes and compression noise. And when I surveyed all the datasets and metrics 2 years ago, about 132 papers, 124 of them were on natural content, and only 8 of them were on consisted of video game videos. And even then, they only focused on compression artifacts. So what's missing is we want artifacts from neural rendering methods, path tracing methods, view synthesis methods, which is something people in this room are interested in. And we want those artifacts on synthetic scenes, which are representative of modern video games. Here's a quick overview of the data set. It consists of 80 video sequences, 3 seconds each, made from 14 high-quality scenes, which we took from Unreal, Unity, and some open-source scenes from NVIDIA, Intel, and Amazon. We use 6 modern rendering techniques. I'll describe them in a moment. And we ran a user study with 20 participants and collected their mean opinion score. Here are the 14 scenes we used in our study. They are, again, some of the scenes that have been popularly used for game engine demos, like Infiltrator, Meerkat, or Zero Day. And we also added some custom scenes, which kind of invokes edge case scenarios, like very fine geometry, bright lights, which leads to ghosting, complex materials, and diverse sorts of motion characteristics. Here are the 6 rendering techniques we used for in our data set. We used neural partitioning pyramids for neural denoising. We used XCSS for neural supersampling, just vanilla path tracing, Gaussian splatting, NVIDIA frame rate up conversion for video interpolation, and Alzar for variable rate shading. And the kind of artifacts we get from these techniques include examples of, let's say, over-smoothing in denoisers. And then we have ghosting, aliasing, and flicker in upsampling, warping artifacts and video interpolation, shimmering and path tracing, kind of texture blocking and variable rate shading, and blurriness and hallucinations and Gaussian splatting. In addition to just rendering these scenes, we rendered them at 4 to 5 different levels of complexity, different levels of quality, to ensure that it contains a mix of almost invisible distortions, barely visible distortions, and clearly visible distortions, modeling the kind of scenarios you often come against in real life. The study protocol was direct rating method. Basically, the study was conducted remotely, and everyone saw 80 videos in random order. And they were played in a loop, and everyone was asked to flip between the distorted video and its corresponding reference version, and rate the video on a scale of very annoying to imperceptible in terms of quality of distortions. Each participant rated each video 3 times, giving us 240 ratings per participant. And the raw ratings were converted to average DMOS scores using Surreal Toolbox, which lets you do outlier rejection and Z normalization. And since it was remote study, we did not have control over viewing conditions. We ensured that all participants had expertise in graphics, and we ensured they tried to simulate situations of PC gaming, how they would play a video game on their display. So here are the key observations from the user study. The first one is that the quality of a rendering technique or a scene does not scale linearly with different parameters of the rendering technique. So just tuning the parameters can maybe not have any effect on the visual quality or can have a huge effect. And also, for example, let's say flicker is visible on one scene due to one technique, it might not be visible in a different scene from the same technique. It's highly content dependent. You can see wide variety of curves across different scenes here. Also, some of the distortions were nearly imperceptible. For example, in the path tracing of jungle scene, for 256 SPP and 64 samples per pixel, they almost the reference quality. Even though if you take the pixel difference between the two videos, you will notice there is errors, which is super important point because this kind of highlights that mathematical error is not same as perceptual error, and we should be using perceptual metrics for determining quality of a video. Another interesting observation, which is very different from the compression papers I've been reading earlier, is that the results were not always monotonic with the decreasing levels of distortions. It is interesting, which basically says that just throwing more and more compute to your methods may not improve the quality, and maybe, in some cases, even make it slightly worse. And finally, this is like a quantification of all the anecdotes I heard yesterday that existing quality metrics do not perform well on computer graphics distortions. So you would expect a human-level metric to have a Pearson correlation of up to 0.96, but the best score we got was 0.78 from HAR-PSI, and even more popular metrics like SSIM, DIST, LPIPS, and PSNR performed even worse. There's clearly a gap between the best performing metric and human, and we want to fill this gap. So let's build a metric that fills this gap. Introducing computer graphics video quality metric. So how do we build a metric? So since we are trying to mimic how humans perceive quality, let's understand how humans come to a decision about quantifying quality for an image or a video. So the way it works is when we look at a screen, just pixel representation of an image, we map that pixel representation through our visual system into some neural representation. And this neural representation is what we end up using to do high-level tasks like rating quality of an image or comparing two images. So what we need as a first step of building this metric is a mapping function that maps from pixel space to some sort of a proxy of this neural representation. And we have multiple choices, multiple approaches towards this mapping function. Usually this can be categorized into three broad categories: psychophysical metrics, handcrafted visual features, or D-feature spaces. Psychophysical metrics, they kind of build upon simple visual models like contrast sensitivity or contrast masking that have been built using user studies on very simple patterns like sine waves or Gaussian patterns. And we try to extend them to complex images. They are amazing at extrapolating to different viewing conditions, but they struggle with modeling higher order vision like motion. Handcrafted metrics, they're simple, they're super computationally efficient, but they require a lot of trial and error to come up with one. And finally, more recently becoming more and more popular is the D-feature spaces. They kind of built on this idea that when we take a neural network that has been trained on some computer vision task mimicking humans, like object detection or image classification, it ends up learning features that are very perceptually uniform, and they kind of translate well to image quality. For example, LPIPs, DIST, and PIAP use 2D CNNs that have been trained on prior classification tasks, and they just work very well on image quality data sets. Since they work so well on image quality data sets, it was a natural question we asked that if 2D CNNs capture spatial artifacts, 3D CNN should capture spatiotemporal artifacts. And surprisingly, this area was very underexplored for videos. So we decided to go in this direction of using D-feature spaces of 3D CNNs. So let's see how we can define a quality metric using a pre-trained 3D CNN, and then we can explore different network architecture designs and training methods and such. So what we do is we take some 3D CNN, we can train it on some classification task. It could be action recognition or video classification, and then we freeze the weights. We do not change the weights at all. These weights do not see video quality data sets. Then we pass both the distorted and distorted and referenced videos through this network, take out the internal activations, find the L2 difference between the reference and distorted features, then weigh every channel separately, differently, using learned weights. I'll come to it in a moment. And then just average it out using mean pooling to get the final video quality. Now, every channel kind of learns a different feature. It could be blurring, could be flicker, could be ghosting. So every channel is differently important to the final quality. And that's why we need to weigh them differently, and hence we scale each channel differently. Note that there's just like around 1,000 channels, so only around 1,000 free parameters, which is different from 12 million free parameters of the network, which we do not train. So we do not overfit on the data sets. All right, so with this, the previous architecture, we tested different configurations. We tried 2 different 3D CNNs, ResNet 18 and C3D network, which have been trained on action recognition and video classification datasets. Then to learn calibrate the channel scales, we used 3 video quality datasets. Gaming video set, which is video game videos with H.264 compression, live stream, which is natural streaming videos, and CG-VQD, which I described earlier. And we had some interesting observations. Different 3D CNNs perform very differently. 3D ResNet 18 outperformed C3D network very significantly. So it's important what kind of a 3D CNN network you use. We also tested 3 different types of convolution techniques, vanilla 3D convolutions, then factorized 3D convolutions, which is basically 2D CNN followed, 2D convolution followed by 1D convolution in time, and mixture of 2D convolution and 3D convolution. Surprisingly, it did not have much effect on the metric performance. And we also noticed that pre-training on computer vision datasets and calibrating on video quality datasets both have a significant effect on metric performance. The most interesting finding in this was even when we do not calibrate this metric on any video quality dataset, basically it's just pre-trained on action recognition, it still outperformed or at least performs similarly to existing traditional metrics, which is amazing because this kind of means that 3D CNN features are very perceptually uniform and hence the metric should be built using them. So here's, we take out some of the best configurations from our experiment and define a CGVQM metric, which we release open source after this talk. So the definition of CGVQM5 is we use 3D ResNet 18, we take the 5 layers out of it. We use R3D, vanilla 3D convolutions. It's calibrated on 20% of gaming video set, live stream set, and CGVQD. And the metric outputs values in the CGVQD scale, which is the perceptually meaningful scale of very annoying distortions, slightly annoying distortions, or imperceptible distortions. We also have a lightweight 2-layer variant of CGVQM, which performs slightly worse than CGVQM5 in terms of correlation with human ratings, but it is more computationally efficient. Here's the same plot I showed earlier with CGVQM5 results. The last 2 ones are us. And we tested it on 3 different statistics: Pearson correlation, Kendall correlation, and root mean square error. And as you can see, we have kind of bridged the gap. We are still not human level, but I think it's an important step forward from the last best performing metric. So we went from 0.78 PLCC to 0.87 PLCC. And to make sure that we are not just performing well on the data sets we tested, we also tested it on 6 more data sets, which we did not train at all. Together, the 9 data sets contain natural and synthetic videos, modern and traditional artifacts, all sorts of viewing conditions, display devices, and such. And again, we consistently kind of performed in the top 25% of all performing metrics across the metrics we tested, outperforming, again, popular metrics like color video VDP, LPIPs, and VMAF. Sorry for so many numbers. Just the last line is interesting. Another very important advantage of a metric is that it doesn't just give you a video quality score for the entire video. It tells you where the errors are and how much the error is. To evaluate how well we were doing on error localization, we use the LockWiz dataset, which is basically 300 images marked by 16 participants each, giving us like probability of detecting errors on every pixel. These are the human marking maps. Then we tested multiple metrics as a binary classifier, whether there's error on this pixel or not. And we used receiver operating characteristic curve and Matthew correlations for this experiment. And again, we outperformed most of the popular error map generating metrics like LPIPs, color video VDP, foveated video VDP, and SSIM. Here's an example error map from our data set and the metric combination. You can see that the metric kind of highlights ghosting in bright regions like car lights and street lamps, and downweighs the same ghosting in car shadows, which is less visible. So is finally the video quality assessment problem solved? Far from it. We still have a long way to go. One of the major problems we noticed in CGVQM was that we are using uniform mean pooling strategy. But the problem is when you have highly localized distortions. For example, in this scene, most of the distortion is on the small red particles you see floating around, there's ghosting on it. But since they only contain very small area of the video, in the final average pooling, they have very little influence on the final quality. So what the metric ends up doing to match human rating, it ends up amplifying errors all across the video, which is obviously suboptimal and not perceptually accurate. We need better saliency-based or attention-based pooling methods, which kind of just focuses on regions of interest. Again, we currently do not have any way to adapt to different viewing configurations. Operating in photometric units might solve that. We only explored training on sports data sets because they were available. But maybe if we pre-train it on synthetic data sets, the learned perceptual features would be even better. Some artifacts are less visible when the objects are really fast moving, but we do not model that. Maybe incorporating optical flow can improve the metric. And our data set is kind of small, just 80 videos. But we were kind of motivated by identifying which areas require further investigation. So what we found out was that variable rate shading, all the metrics kind of agree a lot, probably because the artifacts in VRS are very similar to compression artifacts, while rendering techniques like Gaussian splatting and neural frame interpolation had a huge disagreement between metrics, which means we require further investigation in this direction. And this is the biggest problem we are facing. Full reference metric are great, but they're not super practical. When you want to test your techniques in the wild, reference is rarely available. So we are kind of working on no reference alternatives for this metric. So let's wrap it up. Here are the key takeaways from this talk. Current metrics and video quality data sets do not model spatiotemporal graphics distortions. We introduced a new data set that is built using 6 modern rendering techniques on 14 different scenes. We introduced a new 3D CNN-based video quality metric that can model spatiotemporal artifacts, produces both global scores and localized error maps. It is shown to outperform existing metrics on multiple data sets across different domains. Looking ahead, we want smarter pooling strategies, display adaptive nature of the metric, and we want to work towards no reference video quality assessment, especially for generative pipelines. You can access the source code by scanning this QR code. Thank you.
Thank you for this very interesting talk. We are running a bit late, but we have time for 1 or 2 questions. Anybody? Yeah.
That was really neat work. I think we'll probably use it ourselves. So, do you think that if you use non-experts as your measurement, your stuff would actually be better than is implied by your graphs, because graphics experts are so picky?
Could be. We found a huge consistency between all the, maybe I have a backup slide for that, huge consistency between different participants. And like level of expertise kind of varies between participants, right? And even then we had huge consistency. So I'm assumed that the findings will carry over to non-experts too.
Thanks.
Yeah.
Okay, maybe one more quick question.
Do you want to explain a little bit more about the non-monotonic trends that you saw? The only thing I'll mention is the perception distortion trade-off. I'm not sure if you've come across that previously.
Right. Yeah. Do you mean the perception distortion trade-off paper?
Yeah, exactly.
And so using the metric as a loss function and it doesn't work kind of thing?
Yeah, exactly. The fact that if you minimize distortion, it actually doesn't maximize perceptual quality.
Yes. Again, it's an open problem. And I guess this metric lies in the, it's a distortion metric, not the traditional perception metric in the sense that which compares distributions, quality distribution. So again, referring to that paper, perception distortion trade-off paper, maybe you can use this as a loss function as long as you define that this is acceptable amount of error. And then you can use GAN-based methods or KL divergence to navigate the trade-off curve. But yeah, we haven't explored that. It's fully differentiable. You can use it as a loss function, but it's based on 3D CNNs, which are not super efficient. So you have to find the sweet spot between training and
Thanks.
quality.
Okay, great. Let's thank our speaker again. And while we're getting set up for the second talk, titled Image-Based Spatiotemporal Upsampling for Split Rendering. The presentation will be given by Thomas Köhler, and his co-authors are Michael Steiner, Lukas Radl, Brian Budge, and Markus Steinberger from Technische Universität Graz, Austria, and Huawei.
All right, let's get right into it. So let's start with the motivation for our work. As you might all know, in recent years we have seen a steadily increase for high quality and detailed renderings with like the better hardware and better software each year we add. And on the other hand, we have devices like the Meta Orion glasses, which try to push the boundaries of small, low-powered, head-mounted devices that come with a few limitations, like limited compute power, also the ability to transfer and storing geometry for large and detailed scenes. And so they might even not have any rasterization hardware. So the question is, how can we combine these two worlds to have high-quality renderings on such low-powered devices? And one obvious solution for this comes with cloud rendering, where we simply try to offload the rendering entirely to a high-powered server and then stream the results to the client, which simply can show the images. However, this, of course, kind of needs a low latency to work well, because the motion to photon latency can become quite bad if you have high latency, and therefore the movement of the head is simply too delayed, and that can lead to really bad perception. And especially with these devices that are connected over the internet, mostly in wireless, this is like not feasible in most cases. Same goes for the bandwidth. Streaming high frame rate, high quality videos in most cases simply isn't feasible. Therefore, recent works have explored the split rendering paradigm, where we try to divide the rendering work between the server and the client. In the simplest case, the server would simply render at a lower frame rate, and then we can use some simple technique like time warping on the client. However, especially for time warp, it only accounts for rotation of the head, but no translation, and also dynamic scenes are not accounted for. That's why recent works have tried to come up with better strategies, like Quad Stream by Hladky et al., which use an approximate proxy geometry that can more easily be rendered by a low-power client. Or works like Xargo from Gao et al., which use a mesh-based reprojection to dynamically hide the latency. However, most of these works still need some kind of non-trivial geometry processing or do not handle dynamic scenes. And therefore, we propose a purely image-based method that does not need any rasterization hardware at all, can handle dynamic scenes using bidirectional reprojection, and also we handle disocclusions by using additional auxiliary cameras on the server, and we can also handle dynamic shadows. So let's start with what we are given. This is one of our example scenes that we use for evaluation, and this is rendered at 10 frames per second, basically what our server gives us. And now we want to upsample this to a higher frame rate. So how do we do this? Well, our method is based on the bidirectional reprojection method from Young et al., which basically introduce a one-frame latency to reproject from 2 frames to interpolate and introduce new frames. And this leads to fewer disocclusions as we have more information. For this, they also generate a 3D C motion flow field, which basically for every pixel gives the motion to the next and the previous frame in clip space. And they use these motion flow fields to perform iterative point search and find corresponding pixels in the T and T+1 frame. After this, they compare the results of both images, and in the case of 2 good corresponding pixels, they simply blend the colors. However, if you want to make use of this for a split rendering scenario, there are some challenges we have to overcome. First of all, the method is designed only for client rendering, which means that the start and end position is fixed of the camera, so we only have linear camera motion between 2 frames. However, we want to be able to react to the user's head movement during the 2 server frames that are sent. And they also only use temporal upsampling, no spatial upsampling. And since they can always guarantee to have the next frame, they also do not need any extrapolation, which for split rendering, where we might have some missed frames, is not possible. So therefore, we propose to decouple the scene flow into the object motion only flow field, and the camera motion is then handled by the client. So the object motion is sent by the server to the client, and we then use this together with the current head position. This means that we need to recompute the forward and the backward scene flow for every intermediate frame, and of course, deviating from the predicted head movement from the server does lead to new disocclusions and therefore holes in the image. And that is why we propose to also use additional auxiliary cameras on the server with a higher field of view and also a slight positional offset, which then fills these holes. So this is what the data would look like sent by the server that is used for the reprojection, where we have here the color, the depth, and the 3D object motion for the T and also the T+1 frame. Our algorithm then looks like this. For both the T and T+1 frame, we compute the scene flow to the current interpolation frame using the object motion sent by the server and also the current head position. We then split the scene flow to the current time step, so to the current interpolation frame, and use a 3x3 window search to find a starting point for the iterative point search, which we found that 3 iterations is then enough to find good corresponding pixels. Then we compare the results. We're using the reprojection error and also the projected depth, and then determine the best match. And again, if we find good matches in both images, we simply blend the colors. So if you do this, you can see we already get a higher frame rate, which looks much more fluent. However, you can also see that due to the head movement that deviates from what the server thinks is going to be, we also get some disocclusions that lead to holes. And this is why the third step of our algorithm is to also do the same for the auxiliary cameras. So if we do not find any good matches, we simply repeat the algorithm for the auxiliary cameras until we find a good match. Doing this, now we get rid of all the holes, and it looks much better. However, you might also notice, if you have a look at the shadow of the moving mannequin, that it still looks kind of funky. And this is due to the fact that we only track the object motion and not the entire optical flow of the image. And therefore, dynamic shading changes, such as the shadows, are simply not tracked and only get linearly blended, leading to the results you have seen. So the idea is to separately also track the shadow changes. So our first idea was to simply render the server at the same target frame rate as the client, and then have a per pixel bit string, which basically encodes for each interpolation time step if the pixel is in shadow or not, which if we upsample from 10 to 120 frames would lead to 11 bits per pixel, which is quite a lot. And also, this only works for hard shadows. Of course, for soft shadows, as you can see, this results in artifacts. Therefore, we decided to use more than 1 bit per intermediate frame, so per time step, which basically simply quantizes the soft shadow values. Of course, doing this for 120 frames per second would lead to a lot of data per pixel. So instead, we track the shadows at a decoupled frame rate that is not dependent on the color and server frame rate or the client frame rate. And we found that 40 frames per second is enough to get good results. What I haven't mentioned is that, of course, to interpolate the shadow colors, we also need the minimum and maximum shadow colors that a pixel sees during the interpolation steps. And therefore, we also have to send this additionally. This leads to more data, of course. However, as you can see, in most cases, this data is quite sparse, where here you can see example of what the shadow bit field, the minimum color, and also the maximum shadow color looks like. So the last step in our algorithm is to use the shadow information if there's any present for good correspondences. And when we do this, you can see that we finally get something that looks close to the ground truth. So in total, our pipeline looks like this. We have the server, which gets frequent updates, position updates of the client. Then it renders the data for the color, depth, and the object motion, and also the shadow information. And finally sends this data to the client, which uses the new data together with the data from the old frame and the actual current head position to render the intermediate frames. Of course, sending this much data does require some form of compression and encoding. Luckily, we are purely image-based, which means we can use widely adopted video codecs. For RGB images, we simply use 8-bit HEVC and can also do this with NVENC, of course. Then for our floating point images, like the object motion and the depth, we found that 8 bits are actually too limiting in the precision and lead to significant artifacts at object borders. And therefore, we use 12-bit HEVC, which seems to give a good trade-off between compression and quality. We have one special case, the shadow bit field, which, of course, being a bit field, needs lossless encoding to retain the bit order. And therefore, we simply use the standard compression, which gives a nice compression to latency ratio. For our evaluation, we used 3 scenes. First one here being Robot Lab. The second one you've already seen, the sponsor scene. And lastly, we also tested on a custom Viking village, where we just added some random moving objects. For our setup, we used a 1440p camera, main camera with 60 degrees field of view. We also have 2 auxiliary cameras that render at a lower resolution, 720p, and have 80 degrees field of view. And they are also shifted to the left and the right of the main camera a bit to have some offset. And also they are slightly rotated outwards to cover more space. The server renders the color, depth, and object motion at 10 frames per second, and the shadow information at 40 frames per second, and the client upsamples this to 120 frames per second. Our camera paths for our experimental setup are predetermined and simply use animated paths. However, to simulate the delay of the user's pose, we simply generate the server frames at a 100 millisecond offset. The methods we compare to are simple time warp, a simple forward splitting approach, a re-implementation of the backwards bidirectional reprojection, which means that it basically does not react to the deviating client movement at all, And we also compare to our method with extrapolation only, where we basically simulate a missing frame from the server and simply use the negative backwards flow field of the last frame we have. For our setup, we basically have 3 components. The server data we generated using the universal rendering pipeline from Unity. The encoding and decoding was simply done using FFmpeg, and the client is implemented in C++ and CUDA. The communication in this case was simply done via the file system. So coming to some results, we tested every method on the compressed data using a fixed bitrate of 40 megabits per second. And we used the image metrics SSIM and flip, and also VMAF as a video metric. And as you can see here, compared to the other methods, our method clearly outperforms the easier, more widely adopted methods. Especially time warp and backwards bidirectional reprojection, you can see, perform quite poorly, which is mainly due to the fact that they simply do not align with the ground truth, as time warp does not account for translation, and also backwards bidirectional reprojection does not react to the client's movement. Now you can see some examples. This is what the time warp looks like. As you can see, due to only rotational adjustments, it looks quite choppy. The splatting, forward splatting, looks a bit better. However, the object movement does not look that good. And the bidirectional reprojection does look quite good. However, keep in mind that it does not react to the actual client head movement. And this is our method with extrapolation only. As you can see, it does perform quite well. However, the object movement does look a bit unnatural because simply extrapolating the motion is not as good as interpolation. We also did an ablation on the rate distortion curve, so we tested on different bit rates. You can see in green the ground truth, 120 frames per second, and the time warp in blue, which we tested at different frame rates, and our methods in orange, and also ours in extrapolation in violet. And you can see that we basically outperform the other methods at any bit rate. However, the sweet spot seems to lie at around 40 megabits per second. Coming to performance, as our setup was mainly designed for high flexibility to test this method, it is not optimized for execution speed yet. Therefore, the reprojection currently takes around 2 milliseconds per frame on an RTX 4090. However, we think that there's still a lot of potential for optimization here. In conclusion, we provide an image-based spatiotemporal interpolation pipeline for split rendering, which operates without the need of any geometry, so it's purely image-based. We allow for a free viewpoint, although we do assume linear object motion between frames. And also we're robust to the dynamic soft shadows. We can leverage widely adopted image compression methods, and our results do show a qualitative and also quantitative benefit over the comparison methods. For limitations and future work, we'd like to test this setup on a rear streaming setup, which should be quite easily to adapt. Also, currently we only handle dynamic soft shadows, but there are other dynamic lighting effects that we would like to see adopted as well, like caustics. Also, currently handling multiple light sources simply increases the data sent linearly, which I think can also be done more efficiently. And in general, this method might also benefit from a more custom optimization compression scheme. With that, I thank you for your attention, and I'm open for any questions now.
Thank you. Two very quick questions.
Thanks, nice talk. You addressed shadows and mentioned caustics as another lighting effect. I'm curious if you have thoughts on how this might handle reflections or like transparency.
Yeah, that's another thing. Like Reflections, again, is also not handled currently. So that's also something that would be nice to explore in the future.
Hi, I was wondering about what happens if you're on a moving platform. So it seems you're only sending objects, motion vectors. So if the camera is moving, then it's not like the head movement of the headset. But if you're on a moving platform or in a car or something like that.
Oh, you mean like you're with the headset on something moving, like a train or something?
Yeah, you're on a moving platform that takes you around and that would generate motion.
Yeah, I guess that's kind of a common problem. In this case, it depends on what the headset actually sends, but if it's just the pure motion based on, I don't know, some GPS data or something, then of course this would lead to problems, but yeah, it's probably something you would have to keep in mind, like with normal sensors, like having IMUs and stuff like that, it usually leads to some kind of problems.
So thank you. We are a little bit behind time, so I would defer further discussion to the coffee break. I have some burning questions myself. Let's thank Thomas again.
All right.
Ask our next speaker to set up. So this is now technically the second session of today, consisting of 2 papers in the area of splats and points, and they are from related teams of authors. Our first presentation is going to be Splatshop, efficiently editing large Gaussian splat models. The presentation will be given by Markus Schütz, and his co-authors are Christoph Peters, Florian Halborn, Elmar Eisemann, Markus Magnor, and Michael Wimmer from Vienna, Delft, and Braunschweig. So please take it away.
Yeah, hello everyone. So I'm going to present our editor that can efficiently edit up to around 100 million splats. And we also wanted to make sure that it works in virtual reality, where we can achieve about 90 frames per second for up to around 10 million splats. So this is what it looks like. Here we have it in virtual reality. We have a couple of features that we can use here, like first delete this table here. Then we have an asset library where we already have some pre-cleaned assets we inserted in here, which we can then insert into the scene. Another thing you can do is you can, of course, select stuff and then duplicate it. And here we first get rid of this garden of the table here, and then use this selection and duplication in order to fill the hole with the patches around here. And it turns out that Gaussian splats are really nice for this kind of hole filling, since they're kind of a little bit volumetric, fussy, and if you leave a little bit of overlap, it blends together very nicely in a seamless fashion. So yeah, with a little bit of work here, we end up with a filled hole and a nice lawn in this garden where the table used to be. And yeah, another thing, of course, in virtual reality, select some splats and then you can move them around, place them somewhere else. Yeah, and then you can also do some painting for some important use cases, like paint some graffiti on the walls of abandoned buildings or ruins. Or let's assume this is some kind of statue, an old Roman or Greek statue. And these used to be colored, and with Splatshop we can recolorize them. So the most important feature of all is probably undo and redo. So we took a look at a little bit here on, well, how can we do this efficiently, how much performance does it take, how much memory. And yeah, the easy thing is for selection, for example. If we select something and we want to undo it, we just need a splat mask, a bit mask of 1 bit per splat. That indicates whether the splat has changed or not, and that's how we can undo and redo that. For painting, we need a little bit more memory, so 12 byte per splat for the index of the splat that has changed, and the original color value. For transformation, we would need a lot more memory because we've got positions, rotation, scale, and most important of all, the spherical harmonics. So if you rotate something, we need to update the spherical harmonics. And transforming all of that and keeping the original values would require too much memory. So for now, here we settled with simply storing the transformation matrix and then applying the inverse. So this part here is currently lossy, but for the most part, it works fine. So let's take a little closer look at undoing and the performance of undoing stuff. When we paint something, and we start a paint stroke by pressing the left mouse button or the trigger button on your controller, we first duplicate the color buffer. Then we do the painting, and at the end of the stroke, when we release the mouse button, we then compare the original value and the changed value. And from that, we create a compact diff that only contains the index of the modified splats and the original color values, and that's how we can store this information with relatively few memory if we just paint a small part out of the entire scene. Performance-wise, it looks like this here. So let's take a look at the bottom one, the campus scene with 28 million splats. Here, painting with a brush that covers the entire scene adds about 1.7 millisecond to the frame duration on an RTX 4090. So yeah, that's okay. For compaction, which happens at the end of the brush stroke, we need up to around 9 milliseconds. And that's because we need to do a little bit more stuff here. So first of all, we need to count how many splats have changed in order to allocate as much new memory as we need. So yeah, count it. One kernel counts how many changed. Then we do a new CUDA mem-alloc. And then we have another kernel that populates that stuff. So this can be up to 9 milliseconds, but it's still okay for just releasing your mouse button. And then the undo and redo itself is already it's also quite fast, just about 2 milliseconds if all of the splats have changed. So yeah, there's some more performance measurements of that in the paper for some other stuff for modifying stuff. But let's have a look at the rendering performance. If we want to edit quickly, we also need to be able to render the things quickly. So we've been taking a look at improving things like the sorting of the splats, because with the CUDA-based rasterization pipeline, we need to sort the splats first by depth value and also by tile ID, since we are using some tile-based rendering. And we end up doing a 48-bit sort with a 32-bit key of the depth value and a 16-bit for the tile ID. Now the problem here is that we're not sorting the visible splats. We're sorting the visible fragments or duplicates. So whenever a splat intersects a tile, we create a duplicate. And looking at the garden scene here, from this viewpoint, we have about 1.7 million visible splats. But because of this tile-based rendering, we end up with 4.3 million visible fragments after partitioning the splats. And this is the number that we have to sort, so it's much, much higher. So what we did for the editor here is we split the sorting into two passes, where we first sort the small amount of visible splats by the depth value. Then we create these duplicates, and with a little prefix sum, we can make sure that the duplicates or the fragments, they remain ordered by depth value. And then we do another sort by the tile ID. And yeah, basically what happens, we have this 3D.js rendering pipeline, and we just add another sort in between two stages and make the other sort much, much cheaper. So the whole thing works because the radius sort that's used here is stable. So when we duplicate the splats, we make sure that they are still ordered by depth value, and if we then sort by tile ID, all those fragments that were sorted by depth value, they remain sorted by depth value. And the whole thing pays off because sorting by depth value is more expensive. The keys are less large, and for the radius sort scales linearly with the bits in the key. So we can compute some rudimentary expansiveness value here. So with the original 3D.js pipeline, we have these 4.3 million fragments for the garden scene here. Multiply that by 48-bit, that's how large our key is, and we end up with an expansiveness about 206. And with this two-pass approach, we have 1.7 million visible splats that we sort by the depth value, so with the 32-bit key, plus the 4.3 million fragments that we sort by the tile ID. So with an expansiveness of 123, so quite a bit lower than the original one here. So looking at some performance measurements, for the garden scene that decreases just the sorting time from 0.48 milliseconds to 0.3. For the campus scene, we have much more visible splats in there. And here we have a performance improvement from 1.8 to just 1 millisecond, so about 50% increase. From a close-up viewpoint, if you have another viewpoint from farther away, we have, still have a performance increase of the sorting duration of about 30%. So yeah, this is one of several improvements to the rendering pipeline. Another thing we've taken a look at is imbalanced workloads. Because with the spread rasterization pipeline, the last step is the actual rasterization, where we blend the splats together from front to back for each of the tiles. And the problem here is that some of the tiles have much more splats than other ones. And we only launch one thread block per tile. So some of these thread blocks, they have much work to do. And the GPU has to wait until the slowest running thread block is finished. So in terms of GPU utilization, it looks like this here. So up to about half time, we have a very good utilization. And then utilization drops because all of the cheaper tiles, they have finished rendering, and now some thread blocks are still busy with rendering the remaining tiles here. And this varies greatly from the viewpoint. In some viewpoint, it's not a problem at all. And in other viewpoints, this might add 5 milliseconds to the rendering time, where just maybe 1 or 2 out of 100 streaming multiprocessors is actually doing work. So in virtual reality, this can actually be fixed quite nicely and easily. Here we have the performance measurements, a profile for virtual reality. So first we render the left eye, then we render the right eye. And in both cases, we can see that there's really poor utilization towards the end of the pipeline. So what we can, of course, do is we can use concurrent CUDA streams in order to do some rendering for the right eye, while the left eye hasn't even finished yet. And then we get utilization like this here. So we can squeeze 1 or 2 milliseconds again out of that. There's some considerations for that. And if you just simply duplicate everything, then you also have to duplicate the buffers. For example, we have to do some sorting. We need some intermediate sorting buffers, and we would have to duplicate that. Same for the staging buffers and some other buffers. So with that in mind, we didn't duplicate everything, because some of the stages, they have a fairly good utilization. So sorting could probably be better, but it already has a pretty good utilization. So we do not overlap the sorting. So sorting still happens one after the other. What we do instead is, while the left eye is mostly idle but not finished yet, we already do some sorting for the right eye. So performance-wise, this gives us these improvements here for the garden scene in virtual reality. With the single stream approach, it takes about 8 milliseconds, and with the concurrent CUDA streams, 6.5 milliseconds. Similar for the campus scene, campus has 28 million splats, and here it improves the performance from 16 milliseconds down to 13.8 milliseconds. So another one that I'd like to mention here, so there are more in the paper, but this one is really stupidly easy and works out quite nicely. Progressive spherical harmonics. The problem with spherical harmonics is they're super expensive to evaluate, especially if you use this, which we do from the original approach. Spherical harmonics based on floating point precision, that adds so much memory to the whole thing that this entire rendering pipeline becomes memory bandwidth bound. But the spherical harmonics, their effect is actually relatively subtle, and they do not change the color values that much under slide rotations, under slide movements. So what we can do here is we do some progressive evaluation of the spherical harmonics. So in each frame, we only evaluate the spherical harmonics for 10% of the splats, and we bake that in a color buffer. And in another frame, we take another 10% and bake that into a color buffer that we then use for rendering. And most of the time, that's barely noticeable at all. So even in VR, where you have a lot of head movements, you usually don't notice that. Performance-wise, for the garden scene, we here have performance improvement from 2.6 milliseconds down to 1.9 milliseconds. We also try to go a little further and not do 10% per frame, but only update 3% of the spherical harmonics per frame. And here we have some diminishing returns. So it doesn't improve performance much anymore, but now you can clearly notice that the evaluated color values, they lag behind a bit. So so every 10th frame updating color values, also not just 10% of the circular harmonics per frame. This is kind of a sweet spot that works out nicely. So of course there are still some limitations in future work, and one of them is right now for transformations, when you select something and transform it around, we still update all the spherical harmonics per frame, and this is really super slow. So just updating spherical harmonics as well makes it 14 times slower. So here we also want to do progressive spherical harmonics in the future, where we only update a small amount per frame. And also what we can also do is right now we apply this to translation, rotation, and scale, updated harmonics, but in reality we only don't have to do that for rotation. And for the undo and redo, we also want to take a look at transforming at being able to do the transformation and undoing the transformation in a lossless manner. So, but without having this explosion in memory. So what we could probably do is compress original values. And one thing we could do is we still do it like now, where we apply the inverse transformation matrix and then do some delta encoding just to apply this tiny difference to get a true previous value. And then something that's more of a limitation here than something we can address is what we noticed is when you paint something in this Gaussian splat datasets, basically you're painting into sparse geometry, like doing vertex painting on a mesh model. And the problem here is that all of these reconstruction approaches, they try to fit as few Gaussians as possible. So if you have a very homogeneous surface, a wall with a single color, you might have one splat representing a large region, so of course you cannot paint fine details in there. Maybe something like textured Gaussians could do that, but right now this is more of a limitation. In any case, here one final video where we have this statue here. Let's just assume these are some Roman statues that lost their color values, and in VR we can then nicely recolorize them. And whenever you do something wrong, you can always easily undo and redo, like deliberately wrong here, just brush it and then undo and redo it. Yeah, with that, thank you for attention, and if you're interested in trying it out and the source code, you can take a look here at the GitHub repository.
Thank you, Markus, also for making up for some of the lag we had. So we have more time for questions now.
So nice talk, thank you very much. So original approach was do the style-based stuff, but now everybody seems to be switching to graphics-based splats. So you just cover in a splat with a couple triangles and do 2D. So you considering switching from compute based to rasterization based?
Not really, because I'm not smart enough for Vulkan, so I'm still using CUDA for any kind of rendering, and their tile-based still seems to pay off for everything.
More questions? I don't see one, so I actually have one. Obviously, if you're like cloning parts of the scene or moving it around, the fact that the lighting is baked into the Gaussians becomes a problem of inconsistency at some point. Do you have any ideas on that issue?
Not much. So for the idea here was more to have something like a Photoshop for Gaussian splats. And in Photoshop, we also don't really have real illumination models usually. So for example, one thing, if you insert something into the scene like the truck before, of course the shadows won't match. So we were more trying to have a painting tool to paint the shadows into there to match that. But regarding illumination, we haven't really done anything here.
Okay. We have one more.
Hi, great talk. For your unbalanced workload issue, have you considered just kind of like sorting the tiles? So, you know, the tile, you evaluate the tiles that have the, you know, like the largest amount of splats in them,
Go to the more expensive tiles first, right?
Exactly, and
Yeah.
then fill in the
Yeah,
gaps at the end.
we have tried that, but it doesn't bring that much because they might still take 5 times or 10 times longer than all the other ones. So even if you start first, it doesn't improve much. Another thing we tried is that we use multiple threads per tile. So instead of just one, have 10, do one single tile.
Yep.
And this works. Does improve some stuff. There's also a secret paper from Bernhard Kerbel this year who's doing this. So they kind of did this before us now. We tried it for Splatshop.
Right.
And it did work, but we didn't do it because for inserting some stuff into the scene, we currently rely on having a depth buffer so that we know where to drop things off. And if we do that, if we would use 5 thread blocks per tile, then we have some difficulties finding out where the depth value should be.
Right. Okay, thank you.
Great. So if there are no more questions, then let's thank Markus again. We'll get to the final paper of this session, which will actually be presented from the same laptop, from the same authors from the same group. So the title of this paper is Lidar Scout, Direct Out-of-Core Rendering of Massive Point Clouds. The presentation will be given by Philipp Erler, and his co-authors are Lukas Herzberger, Michael Wimmer, and Markus Schütz, all from TU Wien, I believe.
Yeah. Okay, so I'm going to start with a little overview and the idea behind that, and Philip will take it from there and explore more about height map generation. So with Lidar Scout, we were trying to make it possible to visualize massive point cloud datasets directly, instantly, without having to wait for pre-processing. So let's take a look at some of these datasets. Here we have a dataset with 18 billion points from part of the coast of California. And here, doing the pre-processing in order to create the LOD structure takes about half an hour. Then we took a look at another dataset, Gisborne from New Zealand. And this one already has about 260 billion points, and LOD construction here takes about 2 days. So if you just want to browse through your huge amounts of point clouds and take a quicker look at something, maybe find a region of interest, you have to wait days just for individual datasets. So this is where Lidar Scout comes in. With Lidar Scout, we were able to drop these times down to from half an hour to about 2 seconds, or for Gisborne, from 2 days down to 35 seconds. And with this bit of a startup time, we can then explore these point cloud datasets in real time. So the way this works is actually fairly simple. So first of all, with direct out-of-core rendering, we mean that we don't do any pre-processing. We take the data as it is on disk. Therefore, we also don't need additional disk space, which can always be a bit tricky if you have these large amounts of point clouds data. And we do not compute level of detail structures. So yeah, the first thing we do is we simply have these massive point cloud files, and we do some coarse subsampling, some more or less uniform random sampling from the files from disk in order to quickly generate this overview data set. So here on the top right, we can then see the point cloud in its entirety, the entire extent, and this was loaded in just about 2 seconds. But of course, if we zoom in there, then we will have some kind of garbage. So on the bottom left here, just a couple of points, but we cannot really see what's going on here. So the next thing we do is then the height map reconstruction, where we approximate the height map. It gives us a much, much better idea of what's going on in this region here. And if you zoom in close enough, and the screenshot you are already close enough, then we start loading the full resolution point cloud data from the files. And that way you can already explore the entire point cloud up to the full resolution. So here's an example of what this overview looks like. So first we have this point cloud from disk. It takes about 90 gigabytes. And after dropping, it only takes about 2 seconds until we get this coarse overview of the entire point cloud. And previously it took about half an hour of pre-processing until we could kind of look at something like that here. Then let's take a look at the same thing, but from close up. If we drop the point cloud then we quickly get this core subsample here. But from this close-up, we can't really see anything here. We could make the points a little bigger, but it would still not give a good impression. So what we do now is we quickly create these height maps for the current viewpoint. So we prioritize to the viewpoint. And when we zoom in closer, then we load the full resolution point cloud data. So of course, this has some limitations. So it's not going to replace pre-construction of level of details. Right now here we can look at a full resolution in the center, but we have a very coarse resolution around that. Still, it allows us to explore these data sets in a matter of seconds instead of hours or days. So yeah, and then you can move around a little bit. Okay. So one of the reasons why we made this was kind of for ourselves, because we have all of these huge data sets. And yeah, we want to be able to look at them directly without pre-processing, which also means this has to be possible with the industry standard file formats. And one of the widely used ones here for aerial LiDAR scans is LES. And LSE, the compressed counterpart. And especially LSE is very widely used. It compresses down to about 20 or 25% losslessly. So whenever you download huge, massive LiDAR data, it's either LSE or sometimes compressed, zip-compressed LAS, which is really bad. Yeah, but with these two file formats here that are widely used, we also have AIBs, so the bounding boxes, and these help us for rendering. When we zoom in closely, we have these bounding boxes here, and if some of them are large, if they're near the center of the screen, we can then figure out, okay, this part of the point class belongs to this file, so let's load this file here for the full resolution. So let's take a look at LSE. So basically, we've chosen LSE because that's what's widely used, and whatever works with LSE also works with any uncompressed format like LAS, PLY, or whatever. And the problem with LSE is it's compressed, so we cannot do full random access to any of the points here. But luckily, LSE is compressed in chunks of 50,000 points, which would still be a problem because just setting up creating the decompressors takes a lot of time. If you want to uncompress 250 kilobytes of points, you have to initialize state for 10 megabytes of decompressor. But again, luckily, it uses adaptive arithmetic compression, which means the first point in each chunk is uncompressed, and the further ones are then successively better and better compressed. So basically, this allows us to load a subsample of every 50,000 points from the scene in order to create this coarse overview. For San Simeon, this allows us to load a subset of 300,000 points. And for Gisborne, this allows us to load a subset of around 5 million points. And especially 5 million points, so basically we start from an overview viewpoint when we drop these point clouds, and 5 million points is more than enough for an overview. So the next consideration here is the disk speed. So disks are usually optimized for sequential access, but now we're doing some random access all around the disk here in order to fetch the few uncompressed points. But with SSDs, modern PCI 5 SSDs, they have a theoretical performance of around 1 million random reads per second. In practice, we got closer to about 200,000 because the standard C and C++ APIs, they're not made for random access. They have poor performance here, so we would have to use native file APIs in Windows or Linux. We didn't manage to do that yet. But still, 200,000 per second is fine for our use cases here. So yeah, for San Simeon, it means in 2 seconds, we load these 300,000 points that we have access to. And for Gisborne, we have 5 million points that we have access to. So yeah, Philip is now going to talk a little bit more about the height map reconstruction that we do in order to quickly kind of get a better impression for the whole point cloud, to fill the holes in there, and also improve the quality.
So hi everyone. Yeah, as Markus mentioned, in this example we have roughly 330,000 points. So on top you can see if we would just rasterize those points, it's pretty sparse. If we make the points a bit larger so that it fills most gaps, then you get something like in the middle. And yeah, it's okay, but the height maps are better. You can see it even better in close-up. So on top, it's very sparse. In the middle, you have sort of a closed surface, but it's pretty noisy. So every tree can basically be some point. And on the bottom, we have a slightly over-smoothed thing, but you can clearly see the structures of mountains, for example. Or here an example from the Morro rock. Yeah, you can clearly see the rock in the height map case. So to get the whole reconstruction, we split the whole domain into patches. Every patch is 640 by 640 meters. So for the processing, we have 64 by 64 pixels, and that's already enough. Let's have a closer look at one of the patches. So we take the chunk points for the patch, but not only the chunk points on the patch itself. We need to take care of the boundaries so that adjacent height maps fit together. So we take all the chunk points in a region of 960 by 960 meters. So in principle, we have our scan data, then we get the chunk points, then there's a triangulation step, and then we create rough height maps and textures already with interpolation. So here it's nearest neighbor and linear interpolation, both for the heights and for the colors. We tried several things, but this variant works best. For example, just rasterizing the points didn't work at all. And then in the end, we get a refined height map and texture. And for the refinement, we use a small CNN. And yeah, for the CNN also, we tried several things. The first attempt was with something like PointNet, and it failed completely. It was quite slow and very bad. The next attempt was DCTNet. It's rather used for depth map estimation, so slightly adapted for our use case. And in this variant, we already got better results than linear interpolation. Then I thought, yeah, maybe I can get a very fast, small CNN, even if it might be a little bit worse. But actually, it turned out faster and better than DCTNet. So here's how it works. So as said, we have these 4 inputs, nearest neighbor and linear interpolation, both for heights and colors. Each of those goes into an encoder. The encoders are a few convolutional layers. Each outputs a feature vector. Then we concatenate the feature vectors and compress them further with fully connected layers. That's in 2 steps. So at the end of this merging step, we get again one feature vector, but for all the inputs. Then we have some decoders that produce some intermediate height maps and textures. And here we concatenate on top the inputs again, basically like a skip connection. But since it's concatenated, we have more size than we should have for the actual outputs, so it needs another compression. And in the end, we get our height maps and textures, so the 64 by 64 pixels. Here are some quality examples. So given the chunk points, you can see here the scan for reference. Here's, if we would just take the linear interpolation as we take for the input of the network, it would look like this. So very hard edges and discontinuities, not very nice. In principle, you could also use a cubic interpolation, but you see the very dark and bright spots. The reason is that it overshoots in many cases, and it even overshoots with the height. So there are some random 200-meter spikes in the landscape with cubic interpolation. Then there is high-quality splatting. It's, the colors are pretty good, but it has blobby heights. And we also compared to sort of UNet, so that's adapted from the neural point-based graphics in our framework. It's pretty close to our results, but in some cases it distorts the colors. And the reason is likely that they have just one encoder for all the inputs, so they're basically mixing heights with colors. And here's ours in comparison. Good. So here is a video. Yeah. As shown before, we can just drag and drop. And within a second, it already starts. This is a Gisborne dataset. So this was taken on Marco's PC with a very strong GPU and SSD, but it also works on this laptop, we can show afterwards. Yeah, the laptop is not super strong, just has a 3070 in it. Yeah, you can see which tiles you actually, or you can jump to the tiles, you can quickly see outliers. So if you, well, in future work, you could just view the scan while it's scanning, so maybe stream it from the plane directly. And then you could already see outliers and tell the plane to return to some place. So, coming to the end, there are some limitations. So due to the random access requirement, it basically only works on SSD. You could probably run it on HDD, but it will be very slow. In future work, you could stream it from a server, maybe stream the chunk points or stream the height maps. So people wouldn't even need to download the full data before they know what they need. The network, as it is trained right now, is a little bit dependent on the point cloud density. So it's mostly adapted to the roughly 20 points per square meter of the California and Swiss data set that we used for training. It works also with higher resolutions like in photogrammetry data sets, but it oversmooths, so it doesn't really use the information that's given. And the best way to deal with that is likely to adapt the patch size to the point density. So meaning for photogrammetry data sets, we should use something like maybe 200 meters per patch. Then also future work, of course, we would like to deal with proper or with full 3D scans like city scans. But of course, height maps are not a good representation for this. And another interesting idea would be to use generative models to maybe get more structures in a couple of patches so that you can, for example, see clearly some larger streets or rivers. And we have presented Lidar Scout, a method for quickly exploring large point clouds. We go from the bounding boxes through chunk points and height maps to the actual scan data. And everything is online. You can already download the binary and try it yourself. Code and models are online. And thank you for your attention.
Thank you. We have time for more questions.
Great talk. So with the random access, for those who lived through the days of 300 and 1200 baud modems, when JPEGs came through, they would have an interleaved format, obviously, so you've got an idea. Would you think of proposing a slight variation and pre-process your data so that it was then more friendly for your approach, so you didn't have to worry about the random access so much?
Guess maybe Marcus?
Yeah, so the whole kind of premise here is that we do not do any pre-processing at all. So we take the data set as it is, as we basically get them from the distributors, from the industry, and work with what we get. So of course, with pre-processing, we can always make things better and faster, more suitable, but we try to avoid that.
I was just thinking you could add that in as a separate tool and just add one or more extension on and say, if you pre-processed it, then on the second time you ran it, it'd be so much faster.
Okay, yeah, that could work out.
Great talk, thank you. Maybe some naive questions. You jump straight to machine learning. What if we just use splines to do height maps? Do you need machine learning here? Maybe naive questions.
No, it's a fair question. That was also a reason or a critical point in the reviews. Yeah, actually, we didn't look at splines. Yeah, it should be possible. I would expect that they are somewhat close to the cubic quality, but maybe without overshooting. So yes, would be an interesting idea.
Okay, more questions?
Okay.
Yeah.
Hello, nice talk. You mentioned one of the limitations being 3D buildings and that kind of more complex shapes. Have you looked at all at how to adapt this model for those kind of shapes?
And what? Sorry?
Have you looked at how to adapt the model to work better with more complex 3D shapes like buildings?
Yeah, there are several ideas. So one idea would be to go more in the direction of the neural point-based graphics. So basically just predicting the current view instead of predicting geometry. Or another idea would be to maybe merge height maps with an implicit representation. So we could run some adapted marching cubes, for example. Or maybe go to something, don't know how it's called, like having a height map on every face of a box. Yeah, things like that. The critical point is probably to keep the model fast enough. And that means likely that we need to stick with the image-based approach and learning.
Okay, any more questions? Yes.
In your future work, you mentioned possibly using generative models to infill. What would the goal be? Because essentially these would hallucinate all the features. But I agree it's cool, but I guess what's the end desired result?
Maybe we can show a little bit in the video. We have this updating step. You can roughly see here, there's this blur region in the back. So that's how it comes from the chunk points and the prediction. And the not so blurry part here between the high resolution scan, that's updated. So after we have the high resolution data, we can basically fill every pixel with proper information. So this is already a very big step, and I think we could use this level of detail for the generative models. And this would be good enough, well, for 10 meter by 10 meter pixels that you can represent, let's say, houses, streets, things like this. And with the chunk points, it's just not enough information. So, of course, it will hallucinate a lot, but maybe it has a piece of river here, piece of river there. You could have a reasonable approximation from the model, I guess.
Yeah, also it might be more expensive to generate those pixels than compared to a small CNN or something lightweight, but yeah, cool idea.
Again, I would expect that it's time critical, so it needs to be a very small generative model, probably.
Yeah, like maybe SDXL Turbo or something older.
Great. So any final question? If not, oh, great.
Hello. My question is, this data, where is it stored? Did you stream it, or you kept it on external drive? Or like 2.4 terabytes is terribly large.
Yeah. We had all of this on an SSD, so fairly fast PCI 5 SSD that can load about 15 gigabytes per second, but in terms of random access, about 1.5 million, about 1 million random accesses per second. So there wasn't any streaming involved here.
Okay. And another question, did you use some graphics API for this, or you used CUDA?
This is in CUDA.
This is all done in CUDA.
Because, as mentioned before, I'm not smart enough for Vulkan, so CUDA is much easier. It's easier to draw a triangle in CUDA than in Vulkan.
Okay. All right. And one more thing. How did you decide which points to choose in the first, when you just load the whole thing just to visualize the overall picture?
And it was kind of imposed by the file format because we can only load every 50,000 point, since these are the only ones that are not compressed. And this is also actually a bit wasteful because, of course, if you load 1 point, the SSD loads the entire 4 kilobyte sector. So we would have more data that we load from more points, but we would then have to decode that stuff, and that's simply way too expensive. So we just load every 50,000 point because that's what the file format allows us to do.
Okay, thank you very much.
One more note, we also tried putting the datasets on an external SSD. Then, yeah, of course, it's a bit slower through USB, but it works.
Okay. So I guess then we're perfectly on time to wrap this session up. Thank you all. Thanks our speakers again. And we have coffee break until 10:30.
Okay. Hope you all had a great break. We've had a wonderful hot 3D track so far, and this will be our last talk in that track. So let me introduce Alain Haustetler from Industrial Light and Magic. He's been working there for about 4 years on offline rendering in their shading toolset, which makes sense because Material X, the project that he'll be presenting on, is a very key and influential project in that domain. So please provide a warm welcome for our speaker, Alain.
Yeah, thank you for the introduction. Yes, so in this talk, I'll give a general overview of Material X, mostly aimed at people that are not familiar with the project, so sorry for everyone else. I'll start with a brief recap of the project's history and the important milestone that it has hit so far, and this is followed with an overview of the current state of Material X, and I'll finish with some exciting new developments. Okay, now let's start with the most fundamental question. What is Material X? I think this sentence from the Material X specification captures the essence of the project quite well. In short, Material X is a standard to describe the look of CG objects with the aim to simplify the sharing of assets across a wide range of content creation and rendering software. Now, the project was launched at Industrial Light and Magic in 2012. At the time, OpenEXR was an established standard for image storage, and Alembic was gaining traction as a standard for geometry and animation exchange. However, back then, there was no industry standard to describe the look of a CG object that would satisfy the needs of the of high-end movie and TV production. And this was highly problematic because the VFX work on a project is usually split among multiple vendors, and it's quite common that an asset has to be exchanged between different vendors. It also became increasingly important that assets can be used across different media types, as a number of new Star Wars projects were on the horizon at Lucasfilm at the time. And this meant that it was not just enough to be able to exchange assets across different VFX pipelines, but it was also necessary to do this across the offline rendering and real-time rendering pipelines. And all these factors then led to the development of Material X as a standard for CG object looks across a wide range of applications and media types. And this effort bore fruit as Material X was first used in production on Star Wars The Force Awakens, which allowed the assets look to be transferred for real-time for the creation of the interactive experience trials on Tatooine. Now, around the same time, Autodesk was also looking into solving the problem of portable materials. And after some discussions between Autodesk and ILM, it became clear that joining forces would benefit both efforts significantly, leading to the first partnership in this project. But it was also obvious that an effort like Material X would only be successful through wider industry collaboration. So in the same year, the first version of Material X was Material X specification was publicly released. And it's also interesting to note that ILM initially focused on pattern graphs that are used to define the texture of an object. Early versions of Material X were mostly agnostic to the part of the shader that is responsible for the light transport. And Autodesk, on the other hand, they have experimented with a system that generates shader code based on hierarchies of BSDF building blocks, and these developments later resulted in the physically based shading nodes and the shader generator that exists in Material X today. But I will talk about this more later. Releasing the specification was just the first step. In order to accelerate the adoption of Material X, the project went open source in 2017. and the repository is hosted on GitHub and contains the Material X specification and a suite of tools and libraries that complement the standard and facilitates the integration of Material X into existing applications. From this point on, the project has experienced steady growth, and the pace has picked up quite significantly as more, in recent years, as more organizations have joined the effort. And this has led to a continuous expansion of the specification and feature set through contributions from the community. Here's just a small selection of some of the most important collaborators. The project has not only grown through contributions to its code base and updates to the specification, but it also through industry adoption. Arnold was the first commercial software to support Material X, facilitated through an early partnership between ILM and Autodesk, and it also has played an important role for USD since its early days. And fast forward to today, and we see that Material X has been integrated into some of the most important graphics software packages. It ranges from open source real-time web frameworks to commercial software for high-end movie and TV production. And another important milestone for the project was its adoption by the Academy Software Foundation in 2021, and after an initial incubation period, the project has fulfilled all the requirements to be certified as a hosted project. There has been a strong collaboration between USD and Material X for some years, and this has ultimately led for Material X to become the default in USD in 2023. Yes, but that's now enough about the past, and now I want to switch to the current state of Material X. Material X represents materials as shading graphs made up of shading nodes. The Material X specification defines a set of standard shading nodes of various types, but Material X is more than just a specification. It also comes with a set of useful tools, such as an editor, viewers, and a shader generator. And it also has definitions for common surface shading models, as well as a shader translation system. I'm now going into each of those features individually, and will also highlight some of the newer additions. Yes, so Material X defines different types of nodes, and one of those types are pattern nodes. These nodes usually operate on scalars, colors, or vectors, and they are used to model the texture of objects. Pattern nodes have been part of Material X since the very beginning, and new nodes are added on a regular basis. Now, the current set of nodes consists of nodes for reading texture, applying triplanar mapping, for reading geometry properties like normals, tangents, and user-defined properties. And there's also a set of nodes for procedurals to generate procedural patterns or noise functions. And the outputs of those nodes can be further processed with math nodes or combiners or color correction and similar nodes. And I also want to point out that a new version of Material X was released in January this year that included improvements to the Whirly noise nodes that make it possible for the cells to be filled with constant values. This is, for example, important to model metal flakes. Another addition was a new node for generic color ramps. Yes, and Material X also supports physically based shading nodes. These nodes represent the light transport part of a shader, and so they open up the possibility to fully express shading models with Material X building blocks. And here's a selection of some of the BSDF models that Material X supports. And in the release in January, there was also an addition of a hair shading model based on the Chang hair BSDF. But most of those individual BSDFs are not that useful on their own. This is why Material X also defines utility nodes to combine BSDF. Here's an example of dielectric layered on top of a diffuse BSDF using the layer node. And here's another example of a diffuse BSDF mixed with a conductor BSDF using a mixed node with a 50-50 mix weight. You can see that these combiner nodes make it possible to define complex shading models just with Material X nodes. But Material X does not just define nodes that represent surface-based distribution functions, but it also defines physically based nodes for volumetric effects. And currently, it supports two models. The first is just a simple absorption-only model, and the second is a model for a complete participating medium using the HG phase function, and it comes with the usual parameters for the absorption and scattering coefficients and the phase function anisotropy. It also has a number of nodes that represent emission distribution functions that can either be applied to lights or to surfaces. Here are two examples of emission from a surface, and the first is simple uniform EDF, and the second is a generalized Schlick EDF that has an angle-dependent emission based on the generalized Schlick-Fresnel approximation. I'm just showing this for completeness, but of course, Material X also has a displacement node that can be used to apply modifications to geometry. And finally, I also want to point out that Material X has a small library of nodes for non-photorealistic rendering, and this is becoming more and more important as more animated movies are turning towards stylized looks. This NPR library includes nodes to retrieve the view direction, compute the phasing ratio, and has a Gooch shading node, among others. Okay, now let's zoom out and have a look at what you have seen so far. So we have seen that Material X defines a set of standard nodes for patterns, as well as physically based and non-photorealistic shading nodes. However, this is obviously not enough to define a standard for portable materials. That's why it also defines a schema to describe the interface and additional attributes of nodes and their inputs and outputs. And these attributes are, for example, used for color space management or for handling units and to specify UI-related properties. And the schema also defines how nodes are instantiated and assembled into graphs. And it has a type system with built-in types and a mechanism to define custom types. And all this data is stored using an XML-based file format, and the image on the right is an example of this. So this is a node implemented with, or defined with a custom node graph. And as a side note, Material X also defines an optional extension to assign materials to, or materials and properties to geometry. But this is usually handled by USD or any application-specific mechanism. And to simplify working with those Material X files, a graph editor was contributed to the Material X project in 2023. It lets you load, edit, and save Material X files, and it also has a property editor and a real-time viewer of the material. And it's also worth mentioning that there's an alternative open source Material X editor called Quiltix. However, this editor is not part of the Material X project and is hosted in a separate repository. And apart from the open source editors, there are also some of the commercial packages support Material X graph editing, such as Houdini and LookDefX in Maya. The Material X project has additionally 2 real-time material viewers On the left is a desktop-based viewer written in C++ using OpenGL and Metal, and on the right is a JavaScript-based web viewer based on the free.js framework, and it uses the Material X JavaScript bindings. And both viewer let you load Material X graph and edit their properties interactively. Now, one way to integrate Material X into a renderer is to implement the standard shading node natively, and this is what has been done in some cases. But another option is to make use of ShaderGen. ShaderGen is a library that's part of the Material X project that lets you generate shader code based on Material X graph, and various backends have been implemented over the years. So currently it supports GLSL, OSL, MDL, and MSL. And the idea is that an application would pass the Material X graph to ShaderGen, which would then generate the shader code that can then be consumed by the application for rendering. And this is also what the Material X viewers and the editor do. And it's also worth mentioning that the latest Material X release in March brought some performance improvements to this shader generator. Now, in order to generate any shader code, we first need to be able to, some shading networks. And over the years, various organizations have come up with physically based shading models with various functionality and capabilities. And thanks to the modular nature of Material X, it is possible to express these shading models as Material X graphs. And the consequence of this is that if a renderer implements all the Material X standard nodes, then it is capable of supporting these shading models. And this is an ideal situation from a more material portability point of view. And there are currently definitions for Autodesk Standard Surface, OpenPBR, USD Preview Surface, GLTF, PBR, Llama, and just recently Disney Principle was added, and you can see the shading network on the right. And one model I want to point out in particular is OpenPBR. It is a new open shading model that was developed in collaboration with Autodesk and Adobe and was publicly released last year. And this project is organized as a sub-project of Material X. And in fact, the reference implementation is actually a Material X graph. Now, in an ideal world, all rendering systems would fully support all the Material X shading models. However, this is not really a realistic goal in practice for various reasons. Another difficulty are proprietary shading models, because companies might not want to disclose all the details of their shading models. And even if they could be represented by a Material X graph. And for cases like this, Material X has a shader translation system that uses Material X graphs to translate from one shading model to another shading model. And the shader translation graph can either be hooked into the rendering system directly, so it would run on the fly as part of the shader evaluation, or the translation can happen ahead of time on baked textures. Now, the shader translation graphs that are currently available can translate from OpenPBR to Autodesk Standard Surface, or from Autodesk Standard Surface to OpenPBR, USD Preview Surface, or GLTF PBR. Here's an example of this shader translation graph from Autodesk Standard Surface to USD Preview Surface, shown here in Maya LookedFX. As you can see, the target shader has less parameters than the source shader, or in other words, the target shader is not able to replicate all the effects of the source shader, and for this reason, in this case, the anisotropy is averaged, and the sheen and thin film and subsurface effects are ignored. Here is an example comparison between Autodesk Standard Surface and the translated USD Preview Surface, shown here in the Material X viewer. it's quite close. The only visible difference here is the highlight in the rightmost example. In case of Autodesk standard surface, the highlight is elongated because of the anisotropy, but because USD preview surface does not support anisotropy, the highlight is circular in this case. And we had a project at ILM a few years ago where we refined the shader translation to translate from one of our internal shading models to Autodesk standard surface, and this became part of a larger system to automatically export assets for external vendors. And here's a comparison between our original shading model and Autodesk standard surface with the translated parameters. Again, it looks, it's quite a close match. I think our shader, the highlight is a bit brighter. And here's another example of the BB8 asset with some additional effects like emission and transmission. Again, the results are very close. Okay, now I want to give you a sneak peek of what the future brings. A new shader gen backend has been in the works, and that lets you generate code for the web GPU shading language. And a new pattern node has been added for hex tiling, shown here in the Material X viewer. And both features will be included in an upcoming Material X release. And lastly, I want to talk about the state of Material X in RenderMan. So far, RenderMan has only supported the Material X pattern nodes through USD via its Hydra render delegate. However, it does not yet support the physically based shading nodes as specified by Material X. And this is why we started a collaboration with Pixar last year to finally bring the Material X BSDF to RenderMan XView. And once the work is finished, RenderMan XView will be able to support arbitrary Material X shading graphs. For example, OpenPBR and Autodesk Standard Surface will be supported through the Material X implementation. And the BSDF nodes that have currently been implemented are ordinary diffuse, Burley diffuse, the conductor, dielectric, generalized slick, sheen, and subsurface. And the work to implement the utility nodes to combine the BSDF, so the layer and mixing, is still ongoing. And now I'm going to show you a demonstration of the existing BSDF in action. This was rendered with RenderMan XView in Houdini Solaris. Okay, that brings us almost to the end. I just want to reiterate that the fast progress in recent years mainly comes down to the active engagement of the community, and the stats show us that there has been a constant stream of contributors over the last year, and now we are at over 250 contributors in total. And these contributors are associated with various organizations that are that are helping pushing this project forward. And finally, I want to thank everyone that contributed to this presentation in one way or another. And for more information about the project, visit materialx.org, or if you have any questions or topics to discuss, then drop a message on the Material X Slack channel. I also want to point out that the ASWF organizes regular Dev Days events where interested people can participate in a hackathon to contribute to one of their projects. And the last Dev Days event has resulted in 10 merge pull requests for the Material X project, so it was quite successful. and the next event is on the 25th of September this year. So that's all from my side. Thank you very much.
All right, thank you so much. Do we have any questions from the audience? All right.
Great talk. Can you comment a little bit on the, let's say, whether the gaming industry has seen Material X as a useful tool, what's limiting the adoption?
Yes, yeah. Maybe you've seen on this slide that there has been, it was integrated into Unreal Engine. So like there is currently a way to import Material X assets into Unreal Engine. Now internally it will still be converted into a representation, like a proprietary representation from Unreal Engine, but it helps, like if you have create an asset in a DCC and export it via UST using Material X, then you can import it into Unreal Engine. Yes. I don't think there has been any adoption by Unity so far. Yeah.
Okay, any other questions? Yep.
Thanks for the talk. There is more and more geometry in materials. So you mentioned displacement, but how about vector displacement of fuzz, fibers, like more geometric content in the material? How is Material X dealing with that?
Yeah, Material X itself doesn't like handle the geometry aspects that you would need in another format, right? Or are you talking about shaders to modify the geometry and these kind of things?
No, really the geometric component of materials.
Yeah, that's currently not not covered. Yeah.
Yep, got another question over here.
Thanks for the talk. It's really cool seeing how this has evolved over the years. I was wondering, kind of in line with the earlier question, do you know if there are efforts towards kind of making it more suitable for real-time use?
Making Material X more suitable for real-time use?
Right, just higher performance kind of meant for real-time rendering. It seems like it's mostly designed for offline things at the moment.
Material X was designed with like all kinds of renderers in mind. So it doesn't impose like strong restrictions on like certain shading models. I mean, the Material X viewers, they all run in real time. And it's also okay if a renderer needs to make compromises on shading models just to run in real time. That's perfectly fine. I mean, the goal is not to have total parity across renders. I think that's not possible, at least not right now. So graceful degradation is, I think, the way to go, right? Yeah. So I don't think Material X is really like imposing any restriction that would prevent it from being used in real time.
Hi, thanks. A pretty good talk. It's nice that you're now able to represent all these standard materials via a shading graph. Do you have any information about the overhead that introduced? Like if somebody would just take OpenPBR, write down handwritten, hand-optimized code for the shader compared to the shader network evaluation, and then the generated code with that. Like, do you know if there's any big overhead or downside on that?
Yeah, I mean, there are a lot of different steps involved in this, right? It also depends on how you integrate Material X. Like, are you running the shader generation as part of the rendering process, or are you doing it ahead of time? Yeah, and I mean, the different individual parts of the shading nodes are kind of hand implemented, and then the shader generation aggregates those into like a full shader based on the shading graph. And yes, and then it just produces shader code, and this still goes into some compiler, right? Like in an OSL, it would still go through like the compiler that does like very aggressive constant folding and these kind of optimizations. Yes, so there is an overhead in terms of, yeah, compiling the graph down into shader and then compiling this again into machine code. But then during rendering, I think if the building blocks have been implemented in a proper way, then it shouldn't be too much overhead. But obviously, you can always do you can't be generating a whole, programming a whole shader, just the whole thing, and being able to do optimizations is obviously much faster than if you have a shading graph with individual base building blocks where you can't really do smart tricks. You just have to rely on the compiler and the tools to do the optimization for you. But obviously they can't do any smart things that a human could do. Yes.
Great. Well, I think we're out of time. Let's thank Alain one more time. And with that, we'll move on to lunch. It's going to be in the same place on the 3rd floor. And one note, we are going to have the HPG Town Hall at 12:30, so that is going to be just a half an hour from now. We'd love for all of you to participate to talk about the conference itself. So yeah, enjoy lunch, and we'll see you back here for the Town Hall.
All right, in the interest of time, I'll welcome everybody back from lunch. Glad to have you with us again. I'm your friendly sponsorship chair, here to introduce our sponsor for today's day of the conference, Meta. And we're gonna have a nice 5-minute talk here from Brian Budge from Meta. So go ahead.
Great. All right. Yeah, so I'm Brian Budge. I'm a research engineer at Reality Labs Research. And I'm just going to tell you a little bit about what we're working on over in Reality Labs Research. We're doing novel displays with novel architectures to feed those displays for like AR glasses. We are interested in non-traditional graphics pipelines that need to run at very, very low power, like less than 100 milliwatts. We're doing things like asset compression, neural graphics and codec avatars, shading of human skin and hair. We have some folks in the room doing some of that stuff. Simulation and rendering of cloth, and character motion, animation, and more. We published quite a few papers so far this year, with more to come, I'm sure, and including a couple of talks here. Last year, we announced the Orion glasses, which are sort of like a forerunner of augmented reality glasses from Meta. And I encourage you to go, and if you haven't seen anything about it, go and watch the videos. It's pretty cool. And I want to tell you that we usually start our intern hiring applications like in October for the following year. So if you're interested in interning for us next year, maybe reach out to me sometime like October timeframe at this email address. And we also sometimes do sponsored research agreements with universities. So if you're a university interested in doing research in an area you think will be interesting for us, then feel free to reach out and we can talk about possibly sponsoring some of that research. And I think that's it for me.
So hello and welcome to the real-time rendering session. And the first paper is going to be presented by Peter Shirley from Activision. And it's entitled Spherical Harmonic Exponential for Efficient Glossy Reflections. And it's authored by Ari Silvennoinen, Peter Pike-Sloan, Mikhail Ivanicki, and Derek Novososrasai. Probably wrong.
Thank you.
Yeah, go ahead.
I'm so thankful that he pronounced the names of the author list, so I will not. So I am not an author on this paper, but I do manage the group that most of the people are in who do this, and so I've been following it closely as it developed. And Derek is an academic that we often work with who contributed quite a bit to this paper. And so what we're talking about is something that we do in every video game. Every video game out there pretty much will have this somewhere. Which is, hey, I have some type of environment map, and I need to illuminate things with different glossiness. And this would be like a particular environment map that's illuminating each of these materials that each have a different roughness, basically. And if you're a path tracer, you'd say, oh, I'll just send out a bunch of rays, I'll get some noise, all is good. And the key thing is, the rays are not uniform in this environment map. The reason you see some glossy image in it is because what's integrated over is not uniform. And so that's expensive. Ask any path tracer. And I switched way ahead for some reason. There we go. I guess I don't know this interface of this program made by the company that employs me. So before I get there, look at that integral. And what we have to do is actually evaluate that integral, which is just classic rendering equation. I'm going to integrate over a certain set of solid angles with a weighting function. The weighting function is different for different materials. And there are a couple of key things about most computer games, and certainly our computer game. That environment map is static. And so we can do all the pre-computation we want. The evaluation needs to be 60 frames per second on very low power devices. Like half of our players are on phones. So this is something where we have to be clever to make it fast. And this is the way it is normally done. I won't go into this slide, but this is the way our current game uses things. This has been done this way in lots of games for, I don't know, 15 years or so. And it was introduced by Keras and also independently by someone at Activision. And I won't go into this approximation, but it's detailed in the paper. We're not doing that. There's some problems with it. And basically, the problems are the split sum method has some systematic errors that show up visually. And our contribution is to throw out that split sum and put in something else. I want to say a little point. This is an interesting paper to me in that there's no reason this paper couldn't have been written in 1998. There's no deep learning in here. It doesn't require weird new hardware. It's just a clever way to use math to get something better. So the key word in there that you're going to see is there's an optimization. That's the reason I wouldn't have done this work in the 90s. Is I was like, oh, optimization. I'm not doing that. One thing that is very important, and I actually missed the importance of this when Ari was first doing this, is he takes a log of the HDR image. So one thing, this environment maps to HDR. That causes all sorts of problems. Interestingly, Call of Duty, the main game we work on, is super physically based. So everything's HDR, everything's in real physical units. And so that bright area there is going to be a real problem. And so Ari takes the log, and I'm like, oh, well, you're doing image processing, always take a log, or why don't you better take a power? The log is important mathematically for the spherical harmonic stuff he's going to do, not just for perceptual reasons. So the conventional wisdom often is if you use a high-order spherical harmonic to encode anything about the environment map, you have terrible ringing problems. This is why I always have stayed away from spherical harmonics, is they ring. But it turns out if you use a log, you get rid of a lot of the ringing problems. Now, if Ari does basically what he's doing in the paper, without the log, he gets the thing on the left, which some of you have seen before when you try to use high-order spherical harmonics. And the interesting thing about a log is, later you're going to take an exp to put it back into real units. It will be strictly positive at that point. So you have ringing, well, you have some ringing, but you do not have negative low ringing, which is where you really see obnoxious artifacts. Another aspect of the log, if you're really into signal processing, you would say, oh, you get more of the energy in the earlier terms with the log, and that has advantages. And that's an argument that those of you into signal processing can engage with Ari in. So the key thing he's going to do is a view-dependent factorization. And this is going to look scary, I'm going to warn you, but we're going to make it not scary, because it's really not scary under the hood. So first, there's a trick that's used that is not new, which is you break the reflectance into two components, one the Fresnel edge effects and one the non-edge effects. I'm going to ignore the Fresnel stuff, read the paper for that. And so here's the key bit of the paper. So the base reflectance, this is like the main computation you're going to do. You have a point you want to shade in your program. Any of you who are into rendering have written this function before. You have an environment map. And so look at that function that you have to write. it's v, that's your view vector. There's n, that's the normal vector. And then there's the surface roughness. So this is a very specific BRDF, you know, kind of a classic GGX, Cook torrents kind of BRDF. And so that's the function you need to write. V is a unit vector, so it's 2D. You can think of it as a theta phi. N is a unit vector, so that's 2D. Alpha is a roughness, 0 to 1. 1 is like a diffuse surface, 0 is a perfect mirror. So that's a 5D function. And then a classic trick, I think the first time I saw it was McCool on BRDF 20 years ago or something, is to take a product of two lower dimensional functions. This is used throughout engineering sciences all the time. But the part that I did not expect to work is that you can take a product of two 3D functions with one shared variable and get the amount of complexity, the richness of expressivity that you need. If it was just P of R, H of R for a specific roughness, so take some brush steel that's pretty shiny, hard code that alpha, and take a product of two 2D functions, we kind of know in graphics that might work because of previous work. But adding that alpha in there, I thought that probably wouldn't work out. And you know, I'm sitting here talking, so spoiler, it does work out. So this is where you hit the paper and you say, oh, that looks super complicated, I don't want to do it. Some of this is just the notation in this field is problematic. So if you decode, like, how does this translate into code, things are okay. So I'll go more into these two terms, but note, the function we're writing is the what color is the environment map function, which is that E sub naught. It is a product of two 3D functions. The functions themselves have a certain form, which is the key part of Ari's invention here, I think, is to get this form right. So if you look at exp, that's just calling exp. What's in the parentheses looks like a mess. So let's dig into that a little bit. A key part is that everything is just, you write it into the function is something that's known, except the P and Q there. So ignore everything now. You're writing this function. Everything is straightforwardly written, but there's this P and Q that come out of nowhere. Those are just vectors of floats. So P and Q are the thing that replace the environment map. So there's no environment map in this. They're two vectors of floats, and that will give you the visual appearance if you actually dealt with the real environment map. So it's really just a re-encoding of the environment map in a strange way. That's just a bunch of floats. So, so let's look at just one of those two 2D functions. They look very similar. That VMF of 1 over alpha was used in some of the NERF papers a couple of years ago at CVPR, and so we're using other people's notation. VMF is just a normalized spherical Gaussian, no big deal. If you look at it up there on the upper right, it's not that complicated. You can sit down and write that function or ask ChatGPT to do it. It's not that bad. That circled dot is just I'm doing component by component multiplication. So that VM of F is a vector of floats that you evaluate based on the surface roughness. So it's just floats you say boom, boom, boom for each alpha. That Y is just a spherical harmonic basis function. So you can interpret that as a convolution with the spherical Gaussian if you want to. I'm thinking of it like C code. It's just two vectors of floats. And then the P is a vector of floats that is stored, that you've done in an earlier thing that you replace the environment map with. Environment map comes in, you get a P out. And so that part is just a big vector. Say it's 30 numbers. And yeah, you have two vectors. Two vectors, you do component by component multiplication, you get another vector, you take a dot product, done. That's the entire computation. So in code, it's much simpler than it looks in mathematical notation, as happens so often in rendering. And then you take an exp. Those are the unknown coefficients that you're solving for. And so we need to find those. So we run an optimization. And so you run this big optimization that's a classic thing from your undergraduate CS days. So life is good. You call some Python library. That's all batch as a preprocess. And then if you want to write this out in full vector form with both functions, you get this. But keep in mind, I have two 3D functions. They're just a big vector multiply. The only thing you store are two arrays of floats. There's no environment map. That's the part that was hardest for me to kind of grok in this. It's done separately for red, green, and blue. So just think of it as 3 floating point things, 1 for each channel. And then at runtime, you got to reconstruct. This is the part where we need to be very fast. And one question is just, is this faster than that split sum method, or is it slower? If it's slower, probably not going to do this. And so if you look at this and think back to what these things are, they're just vectors of floats. It looks like it could be fast if there aren't too many terms. Let's just say the Fresnel tail reflectance is a simple modification of that that is not very expensive, and it's accurate enough. Well, that's all we'll say about that, just in interest of time. And then I ran this on a bajillion different environment maps and said, how good are the results? And let's just look at one particular result. If you look at the reference, it looks different than either Ari's new method or the split sum method, which is better as a matter of opinion because they have different artifacts. As I look at a bunch of them, you can look at a bunch of examples in the paper. I think that the new method looks better. Numerically, it looks better. I'm always a little shy on all these numerical tests, but it does work better numerically 95% of the time. So the question is, does it take more storage, and is it faster? Better we can debate. I think it is. In this particular example, you can see that the hours lacks some of the features that the reference has, say, on the right. The split sum overemphasizes the features, which looks better. Subjective. Those are the what would be called systematic error because it just keeps showing up in a very particular way. The performance, interestingly, Ari's new method is faster, which I wasn't expecting because I saw a lot of vector operations there. Seemed like it would be tough, but with 33, I think, is the number of coefficients in that those two vectors that he computes, P and Q, it ends up being faster, which was surprising to me. I think that was on a, was it on a 3070? I can't remember, some standard GPU. It has a lower measured error on most cases. Their distribution is very non-uniform, so it's probably the perceptual nature of it that is more important. That they look especially bad for that particular case. That's a bad case for the split sum. But there is a big limitation. So let's review. There's a pretty simple method that just is a drop-in replacement for the standard method. It's faster. It takes much less storage. So I think 200x less storage, because just replacing a cube map, a multi-level cube map with just 2 arrays of floats, big win on storage. But there's a certain near mirror-like reflection it just can't do, because you can't represent that with this spherical harmonic approximation that just doesn't have enough detail terms for it. So if you want this for perfect mirrors, just doesn't work. You do have to, therefore, in our game, maintain a high-resolution environment map, so that 200x speed our storage improvement turns into like a 30% storage improvement unless you can replace specular objects with something like ray tracing, which I, of course, think you should. And so the roughness values in our pretty standard material model is you lose perfectly specular to roughness 0.25. Oh, and this also shows that as you start taking fewer coefficients, you lose detail. So 33 is the magic number that gives, in Ari's experiments, what he thinks is good resolution. So in summary, I'll let you read that. On real models, it does seem to look better to me. We haven't deployed it in the full game yet. It's implemented in the full game, but it hasn't been tested on the full model. So, talk to me in a year and I'll tell you if there were any surprises. But so far, nothing scary has appeared. And thank you, and we'll see if this video plays in PowerPoint. I've been doing this for decades. I've never had a video play successfully in a talk before. This is real progress, so we can have questions now.
Thank you very much. Are there any questions?
This is quite astonishing. I almost don't believe that it's faster. I have to wrap my hand around it. Also, one of, significant contribution to this problem in I don't know how many years. A question could be, like with the cube maps, we had a lot of technology and hacks and whatever developed. One significant one that we had is this notion of localized or parallax-corrected cube maps. Is this something that you don't think is necessary because you're just baking enough to interpolate, or do you think that this thing could also extend to those kind of corrections?
I would say I hope it's not necessary, but unknown. You have a very good point that it's always tough to replace mature technology with something that may lack these types of optimizations. Ironically, the lack of ability to handle the low roughnesses probably helps this a lot, right? So blurring, as long as the blurred stuff has the right dynamic artifacts, it might work okay, but unknown. This is the short answer. And also, since I'm not, this isn't my paper, I just manage the group this is in, I can say, I agree with you, I'm shocked. There's a real advance that can happen in this area. And I had trouble reading the paper because I just couldn't quite grok that, you're actually getting rid of the cube map. This just was hard for me to accept.
There is much more to do because all our math, there is a lot of wrong that we still do, but this is amazing.
And interestingly, the memory footprint is the same as a 3x3 cube map. So that's pretty blurry cube map. Yes, sir.
Works? Yeah, it works. Nice talk, great paper. My question is, so in the numbers that you've shown for the roughness, you go down to 0.09, but artists don't like to be constrained, and they like to operate in that high specularity range. My question is, was it exposed to artists just to see if they're fine having either ray trace or purely specular, or higher roughness than 0.09?
The answer is no. And so right now, for really low roughnesses, we would have to do something different. And so when I just flippantly said I think it should be ray traced, what happens if roughness is like 0.05? Is a little path tracing perturbation going to be low enough noise that it would be acceptable? Unknown. I would say that one of the troubles we're experiencing in games, but it looks to me like every AAA game has this, is every component of the rendering has noise. And all of that noise goes in together and goes into denoisers that are still under development. And so you often are getting surprising noise artifacts. And how problematic are these? And so when I look at them, sometimes I'm like, wow, those are really bad. And when my child looks at them, she says, those are fine. Just like my generation said, edge crawling is fine. So I do think this is like a real question in our industry, though, is just how much noise is too much.
All right, I think we have time for one more question, if this...
Thanks, it looks really great. You said that you had basically 3 vectors for red, green, and blue. How much correlation is between them, and is there an option to squeeze more, get more reduction?
Right now, it's just done separately, as my belief is, from what Ari has told me. I haven't looked at that portion of the code, though, so that's not an authoritative answer. But I think they're just done completely independently. And you probably could squeeze some more out doing something there.
All right, let's thank Peter once again.
Also, I want to acknowledge especially Peter Shirley.
All right, so for the next talk, it's called Fast Planetary Shadows Using Fourier Compressed Horizon Maps. And the presentation is going to be given by Jonathan Fritsch. And his co-authors are Simon Schniegens, Fabian Friedrich, Markus Flatken, Martin Eisenman, and Andreas Gernt.
Okay, 1 second, please. So, okay. Thanks. And let's get right into it. I think we don't need that much explanation on why rendering of shadows is interesting. So I'll focus more on the kinds of shadows which we want to render, which in our case is the rendering of fast shadows, so real-time capable. Specifically also targeting virtual reality systems. And we want to render the shadows of large-scale planetary terrains, specifically here the self-shadowing. And as we're dealing with planets, the light source most often is the sun, so we have an area light source and require soft shadows. And large-scale means here that we have amounts of data in order to represent these terrains, which aren't really feasible to store in memory. So we require some kind of out-of-core storage and load this terrain data in at runtime. And because of this, we want to minimize the amount of extra data which we load in order to, for example, render shadows for out-of-frustum occluders. And one historical solution to do this, which is able to encode all the occluder information locally, is the horizon mapping algorithm implemented and presented by Nelson Max. So here I'll just give a short introduction of how this algorithm works, and then in the next slides I'll go over our method and how we extended it. So first of all, if we're talking about horizons, this means the border between the visible sky and visible ground as viewed from a given point on top of our terrain. So here we have this bottom black dot on top of our terrain, and this blue line then marks the border between visible hills and the sky. And now, if we have terrains which are represented purely as 2D height maps, we can have neither overhangs nor caves in our terrain, which means that we can put our horizon function, we can plot it in polar coordinates as a continuous and periodic function, such as here at the bottom. And if we have such kind of function for each point of our terrain, we can, at runtime, easily render shadows by just comparing the position of our sun to the position of this horizon function and check if it's above or below this line. If the sun is below, we are in shadow. If it's above, our point is illuminated. Now, naturally, storing a horizon function such as this at the bottom is not that feasible if you're dealing with huge amounts of terrain, because this is made up of 360 samples. So even if we were to store these at 2 bytes, we still have about there should be half a kilobyte of extra storage per pixel, so not really what we want. Because of that, in traditional horizon mapping, so the one presented by Max, this horizon function was reduced in resolution down to 8 samples. In our case, in this paper, we're using 12 samples here, because that more closely matches the memory footprint which our method will use. So in this case, this horizon then would look something like this. So we have regularly spaced support points, and between these there's some linear interpolation. And as you can see, this in some cases matches features quite closely. Here on the left, the first peak is represented well. However, other peaks are cut off. So here we want to improve on this and more closely match this function, match this horizon function. And for each of these support points here in the horizon, additional texture layer, so to say, is saved. So we get some additional images here at the top, which are then used during rendering. Now, our method is essentially the same concept, but we present our horizons as a truncated Fourier series. And we store these Fourier series in a single multi-resolution texture file. A single file meaning here that we have 32-bit per channel and 4 color channels. As you can see in the bottom plot here, we do lose some of our high frequency features of this horizon, as would be expected from a truncated Fourier series. But in exchange for that, we match the horizon, the underlying horizon shape more closely. And during evaluation, we could show that across various azimuths, the average accuracy was higher compared to traditional horizon mapping. So our method is essentially divided into first a pre-processing step, shown here by these blue boxes at the bottom, and then some runtime steps which are carried out in the shader. The slightly paler boxes here mark steps which are applicable both to our method and also to the traditional horizon mapping or other possible horizon representations, while the solid colored boxes are essential to our method. So now I'd like to go step by step over these pipeline steps. And we start with the initial calculation of a high-resolution horizon function, which we use as a starting point. For this, we simply iterated over each pixel of our height map and traced geodesic lines across the terrain in 360 directions, so 1 degree steps. And note here that we have to trace geodesic lines and not lines in texture space because we're dealing with map projections for the complete planetary terrain, or for example Mars. Straight lines in world space actually get projected to some curved lines on top of our map texture. Now for our proof of concept, here we could use a brute force approach and get some usable data sets, but for applying this to highly detailed terrain models, we recommend to use more efficient algorithms such as the one presented by Stuart. Now with this initial high resolution horizon map acquired, we can start with a discrete Fourier transform in order to transform our horizon function into frequency space. Here, first of all, this is initially lossless, so we don't lose any details, but we also don't lose any memory requirements. So in the next step, we then truncate this Fourier series down to 16 coefficients. As you can see here in the bottom plot, in the beginning, if we start removing coefficients, it doesn't change much, but in the end, there's quite a lot of high-frequency details which is lost. And interestingly, the effect on the shadow here on the right is pretty much the same. So we don't get any discontinuities. It's just that the contour of the shadow changes and gets more smoothed out, which is quite good that we don't get any artifacts here, even though we do this without taking into account any neighboring pixels. Then in the next step, we also reduce the bit depth a bit, because previously we dealt with 64-bit floats, which isn't really that nice to use on graphics cards. So first we went down to 32 bits, and then further to 16-bit per float. Here, when going down to 16-bit floats, there weren't any noticeable changes, whereas going further down to an 8-bit normalized representation, we got some noisy artifacts for our method at the top, and some banding artifacts for traditional horizon mapping, which is why we opted to just stick with 16-bit floats for now. Although here there may be still some room for improvement and further work. Now, the next step is the key part of our method, which allows us to actually save a lot of memory compared to traditional horizon mapping, or achieve a better performance at the same memory footprint. And here we take our previous stack of Fourier coefficients, represented by this tall stack here on the left, and then decrease the spatial resolution of some of our Fourier coefficients. To decide which coefficients we want to reduce in resolution, we took a look at the summed up contributions of each coefficient, which is plotted here in the graph. So you can see in blue, this line marks the sum of the basis functions corresponding to the first 4 Fourier coefficients. And you can see that it by far dominates the horizon shape and contributes the most effect to the horizon shape. And then with increasing frequency, obviously the frequency of these functions rises, but the magnitude lowers. So in general here we can say that the total effect of these coefficients is less. And because of that, we can manage to introduce a bit more error into the textures here compared to what would happen if we were to decrease the resolution of the low frequency coefficients. So in conclusion, we have this high resolution, these low frequency coefficients which we store at high resolution, and for the higher frequency coefficients we reduce the resolution. Especially for large-scale shadows. So for example, here in the bottom right, we have some kind of mountain with a cliffside which casts a shadow towards the top left. We can see that at 16 coefficients at full resolution, there's a bit of detail in there. And when going down to this multi-resolution pyramid, we barely lose any of these details. Whereas if we would use 6 coefficients at full resolution, which is roughly equivalent in total memory used, we do lose quite a bit. So this is why we stick with this middle solution and use the 16 coefficients stored in our multi-resolution pyramid. And now this pyramid, then we pack into a single texture file, where each of the color channels contains one of the complex Fourier coefficients with 2 16-bit floats packed into a single 32-bit float and then unpacked during runtime in the shader. And the decreased resolution images are packed into the mid-levels of the texture. Now at runtime, we load this, and then in the shader, we have to actually compute this intersection area between the horizon and the sun in order to calculate soft shadows. Because the attenuation of light obviously depends on this intersection area and how much of the sun is visible to our point on the terrain. In order to do this, we have to reconstruct the horizon shape, at least at some parts of the sun. And this is done using the inverse discrete Fourier transform. So we sum up the basis functions according to the values of the coefficients at these steps, and then can reconstruct the horizon like this. However, in order to reduce the computational load of this step, we don't reconstruct the complete horizon inside of the sun, but instead use some approximations, which are shown here. So first of all, we implemented the approach which was used by Nelson Max in the original paper, which we here call a constant altitude. This essentially takes a single sample of the horizon at the center of the sun, and then assumes that the horizon is roughly of constant altitude across the solar disk. Then we also implemented some methods where we take multiple samples of the horizon. First of all, with this circular segment variant, we take one sample to the left and one sample to the right of the sun, and put a straight line through it, and then calculate here this circular segment below this line, which then assumes that there's a constant slope between these points. Now, as you can see here, this then is obviously able to miss some interior features, like this peak here, which is in the middle of the sun. And additionally, we also implemented this series of vertical slices, which essentially just numerically approximates the integral of this intersection. So by increasing the number of slices more and more, we get closer to the exact integral. Now in experiments, we observed that this constant altitude function performs quite well and is what we would recommend to use for most cases where performance is critical, because as it only uses a single horizon value, it's quite simple to reconstruct. But if performance is of little regard, we can switch over to this vertical slices approach and increase the number of slices to get more accurate penumbras for our shadows. Now this part about the performance brings us to our next part, namely the evaluation of our method. Here, first of all, we did some performance performance benchmarks. And for that, we implemented our method in Cosmos Scout VR, an open source application for rendering planetary surfaces and planetary datasets. We rendered a scene at 1920 by 1080 on 2 different test systems, one using an entry-level notebook using an RTX 2050 and one on a high-end desktop with an RTX 4090. And then we proposed different quality presets, where for one, we varied between using the vertex shader and fragment shader. As you can see here, the vertex shader introduces some stair artifacts, which are because of the underlying geometry of our terrain, which is rendered here, whereas the fragment shader has a smoother shadow contours at the cost of higher performance impact. And additionally, we also did some tests using only 8 of the 16 available coefficients, which then results in slightly changed peaks of these shadows, but again, brings in some performance savings. But all in all, from these measurements here, you can see that on a high-end graphics card, this has very little performance impact and runs well under 1 millisecond. On mobile graphics cards, I would say that this fragment shader and 16 coefficient configuration is not that usable, unfortunately, but if we stick to, for example, 8 coefficients in the fragment shader, we can still get some quite nice shadows in good times. Then furthermore, we did some evaluations of the visual quality of the shadows produced using our method. Here we computed shadows for a top-down view of 5 different test scenes. The first 3 of them are of real-world terrain from the Martian surface, whereas the bottom ones represent some worst-case scenarios and highly synthetic data sets. We rendered shadows as ground truth using traditional horizon mapping at 360 horizon samples, which is essentially equivalent to doing direct lighting via ray tracing. And as a reference, we use traditional horizon mapping at, as I said, 12 samples, which actually is slightly more memory than our method, evaluated at 8 or 16 coefficients. For these images, we rendered hard shadows only without any diffuse lighting, so we get these simple binary shadow masks. And then we did pairwise comparisons between our method and ground truth and reference and ground truth. Here we evaluated the SSIM, LPIPS metric, and we calculated a pixel error rate, which is just the ratio of incorrectly shaded pixels, so both false positives and false negatives, compared to the total number of pixels. As you can see here in the LPIPS plot, the magnitude of these metrics is not really comparable between scenes because of the different amounts of shadow that is present in each scene. So here at the top, we further normalized this pixel error rate in order to put the traditional horizon mapping method at a value of 1. And as you can see, our method at both 16 and 8 coefficients consistently produces fewer incorrectly shaded pixels compared to traditional horizon mapping. Another nice thing observable here is that these error bars mark the 80% percentile, and our method performs much more consistently compared to traditional horizon mapping. So this also results in a nicer rotational behavior if we change the azimut during rendering. The only exception where our method performed slightly worse than original traditional horizon mapping is for the LPIPS metric in this highly artificial peak scene, where we get some slightly higher values, but across all metrics and all other scenes, we performed better. So, to conclude, we presented Fourier compressed horizon mapping, which is an extension of the original horizon mapping algorithm by Nelson Max. And by representing local horizon functions as a truncated Fourier series and storing that in a multi-resolution texture file, we can produce more consistent and more accurate shadows. And an implementation as part of Cosmos Scout VR showed that we can achieve adequate performance with this and are well real-time capable. Still, there are some possible improvements to our method and also some additional alternative Horizon representations, which we would like to take a look at, for example, using neural networks to sort them. And with that, I would like to thank you for your attention and show here a short demo video from the Cosmos Scout VR implementation. Thank you.
Thank you, Jonathan. Any questions?
Thank you. This is really cool. So I was wondering, you mentioned at the very beginning that this is intended for more of like soft lighting. So when you have really harsh directional lighting, at what point would you say that this method just is completely unacceptable, or would it still be a decent approximation even under like direct lighting?
Well, under the visual quality, we actually evaluated under hard lighting, and we assumed that soft lighting would rather hide errors instead of adding additional errors. So the results here shown in these plots is actually for direct hard shadows. And yeah, here in some scenes, this obviously looks a bit strange, especially for these highly artificial scenes. But for the natural scenes, this does produce pretty consistent and reasonable shadow boundaries.
Right, I'll ask one. Yeah, when I saw Fourier analysis and a hierarchical representation, it got me thinking of like wavelets.
Sorry?
So I was thinking, could you adapt your method to use a Haar wavelet representation instead of Fourier?
I think that would definitely be possible to use here alternative representations, and that's also something I'm quite interested in checking out. For now, we settle on these Fourier functions, as the inherent periodicity is quite nice to have. And yeah.
Nice work. With the particular application that you have here with these planetary scale renderings, sometimes I imagine you have very distant views. So in this context, pre-filtering of the shadows becomes a concern, so that you can account for all, like the average of all the shadows that you get in like a square kilometer region on the planet surface. Is that something that you have thoughts on how to do that?
Well, we actually kind of did this because the application uses this level of detail system where we have this quad tree of tiles, and if we get closer, these are dynamically refined. And for this, we actually just did linear interpolation or applied a box filter to our higher resolution horizon maps, and then made them downsampled them in order to get these lower resolution samples. And as you can see here in this shadow right in the middle, this works reasonably well and produces not that much popping here.
Nice, thanks.
All right, I think we need to move on to the last presentation. So let's thank the speaker again. So the final presentation of this session is entitled Real-Time Rendering of Animated Meshless Representation. And it's presented by Pacom Leton and co-author Thibaut Tricard.
Okay. It recognizes.
HDMI is a bit of sacred cable, right? Maybe another port. Okay.
Yes. Okay. Yeah, sorry for inconvenience. So thank you for the introduction. So let's start with a quick preview of what we wanted to achieve with this paper. So we wanted to be able to animate some meshless representation in real time. Here it's a sign distance field that is modified by 3D procedural noise. The original SDF was from Inigo Quiles, and I thank him for letting me use this sign distance field. So first, let's talk about what we mean by meshless representation. So this is all the geometric representation that are not based on a mesh. So for example, there is implicit representation, like a sign distance function, a procedural trendiness, or density function. They are characterized, but the definition of the implicit, it's defined by a function where you can evaluate everywhere in the space, and it tells some information about the geometry. For sign distance function, it tells the distance to the geometry. Here it's a 2D sign distance function of a art. The advantage is that it has a low memory cost, as we only store some function with some parameter. Because it's procedural, you can potentially have infinite resolution. You can zoom in as much as you want on the geometry and still have rich detail. Well, it's more costly to render than a traditional mesh, but there are a bunch of papers to make it fast. And one thing that is troublesome with implicit is that it's difficult to animate. It's well defined for a space, but because you don't have direct handle to modify the function, and moreover, there's a limit number of parameters of each function, you can't animate it like you would want for a character. Another representation, it's voxels. On the opposite, here we store everything. It's a meshless representation, but where we store the data into a 3D grid. Because it's stored, it's fast to evaluate. It can represent volumetric data, like a cloud here. You have an easy way of computing a level of details. And one thing that I particularly like with voxels is its ability to be dynamically updated. Like in the game Teardown, you can just destroy and edit the voxel in real time without to take into account the topology of the object. If you want to create a hole into a 3D mesh, it's kind of difficult. You have to be careful to the topology. And once again, it's difficult to animate. The reason here is that the position of a given voxel is fixed by this position into the 3D grid representation in the memory. So you can't directly animate it. You can, of course, move change the voxel with like free animation, like free dynamic, but you can't really do some character animation. So we have both great representations that are not based on the mesh, and they all have the same default that it's difficult to animate. And our goal in this paper was to make it easier to animate, and especially in real time. And if possible, we want this to be compatible with the classical animation workflow of an artist, and also compatible with the classical rendering engine that people use. So it's not a new subject. There is some research on it. I will just go over a few relevant things to our method. So the first idea is just to forget about other representation and just convert everything back to a mesh. And if you convert to a mesh, it's then easy to animate. You can use the classical tools. But of course, it's not a satisfying solution. It's a hard problem for complex surface, even impossible for some volumetric data. And you lose all the advantages of other representation. And you can do something a bit different, is that to embed the geometry inside a triangular mesh. Just like with a cage-based deformation, where you have a geometry for something classically done for complex triangular mesh, where you have a really high number of triangle. You define the geometry in some response. You encase it into a coarse triangle mesh. You bind some weight, and then by animating the coarse cage, you can directly deform the triangular mesh, the complex mesh. And we want to do something a bit similar for meshless representation. So we have our geometry here. It's a sphere well defined in some respo space where you can render it. We encase it with cage-based deformation, and we deform it, and we hope to deform the meshes. But it doesn't work directly because you don't know how to apply this direct deformation on the meshless representation that is only well defined in some respo space. So if you want to tracerize that across the cage, you don't know how to render it. So the idea that was used is to do some kind of inverse mapping of the deformation and some curve path tracing. So when you have an array that cross the coarse cage, you just compute the equivalent ray in respo space that is curved, and then in this well-defined space, you can render the meshless representation, or the voxel grid, or the implicit. And that's something that that was already done by a few people. Here is they have a complex cage, and in order to deform the ray they deform the ray iteratively by creating the Jacobian of the deformation at each point of the ray marching, and thus bending the ray iteratively. But because there are some marching and they have to query a lot of Jacobian, it's not really compatible with the real-time GPU, so it was not satisfying for us. And it doesn't support self-intersection, which is a bit a limitation for if you want it to be used by an artist. And, yeah. Another solution is the juxtaposition of tetrahedral cage. The idea is that within each case, it's easy to invert the deformation, so you don't have to do it iteratively by remarching. But here in this paper, they're still doing it iteratively. There's some. The main difficulty with this kind of approach is to know in which tetrahedron is each point of the remarching. And just a quick note here: the deformation became piecewise linear and not curve linear. I will get to that later. But here, in this paper, they still use the paradigm of remarching. They start from the camera and march iteratively. So they need some kind of acceleration structure to know in which tetrahedron they are into. And it's quite slow if you have to have BVH, and it can be quite slow. And in graphics, there is another paradigm that it's not directly remarching, that is really fast, is the rasterization. So ideally, we would like to rasterize all this tetrahedron in order to compute everything in parallel in the same time. So that's a problem that was partially solved by my co-author last year, presented at HPG. I will just get a bit into the detail because it's a building block of our method. So the idea was to rasterize the volume. So ideally, we would like we have some tetrahedron that are stored in the vertex buffer and in this buffer. We want to pass it to the rasterizer and then have some interval shader that is close to what does the fragment shader. But instead of having just a 1 point and computing its contribution, it will compute the contribution of all the ray passing through the tetrahedron. And so you have to compute an interval contribution. To do that, he proposed to encode the tetrahedron into a mesh shader in order to rasterize it. To encode it, he just transformed each tetrahedron into some triangle proxy that will have some attribute that will encode the front and the back of the tetrahedron. So I can start with our method now. So the quick overview of what we want to do. So we have, just to recap, we have a meshless shape that is well defined in some Westport space. Here it's a voxel grid. We ask for an artist to provide an animated quartz tetrahedral cage that will define how each point in space will be deformed. And our method will be able to render the meshless shape animated. Here it's the voxel grid that is deformed. Just quickly, our method still needs an animation of the quartz tetrahedral cage, but it's not really complicated. It can be done really easily. Just describe here quickly how we done it, but it's accessory to the method. If you have a better method, please do so. So the idea is to start by creating a tetrahedral cage around the geometry. Here, because we had a sign distance field with a conservative marching cube, we can have this shell. We rigged the triangle cage in Blender. We tetrahedralized the interior of the cage with the elaborated gem, and then just propagate the animation weight with the bounded biharmonic weight paper. And that's it, so we just animate it. And yeah. So it's exactly the thing that artists are used to do with a triangular mesh. So then next I can talk about the rendering pipeline. So there is 3 big stages. The first one is a compute shader that will compute the actual animation, just like you will usually do with a vertex shader. Then we have the interval shading that will rasterize all the tetrahedron. And then in the fragment shader, we will compute the contribution of each tetrahedron. It's just the same fragment shader that we use usually to render this respo space. It's just that the interval shading, we provide the entry and exit point of each tetrahedron. So the animation stage just animate the quartz tetrahedral cage. It's the same skinning algorithm that we are used to do. Then we rasterize with the interval staging approach. So for each tetrahedron, we splat it, we decompose it on future angle, and we rasterize them. But we need some attributes in order to retrieve the entry and exit point of the ray passing through the tetrahedron in the RESPO space. So you need all these attributes. It's quite a lot. So there is there is attribute the x and y from the coordinate in project space. That is the 3 coordinate. You need also to pass the UVW coordinate in RESPO space and the Jacobian of the deformation to make the correct shading. The way we can't directly pass this attribute. You need to encode it in order for the rasterizer to interpolate it correctly. The main issue is that you have to interpolate the front and the entry and the exit point, so there is 2W, so you can't really do it classically. You have a bit of encoding. More detail can be found in the paper. And then there is a fragment stage. So for arrays that cross or deform a tetrahedral cage, each fragment invocation will solve the contribution of a small segment of the ray. And of course, and then with the ROP operator, we'll compose all this information in order to have the full contribution of the ray. Just a quick note on the number of tetrahedra we use for the animation. Here you can see that if you have way too low, because if you have a low number of tetrahedra, you will see some age of for the animation. But with only, as the animation is a bit low frequency things, with a small number of tetrahedra, we can prove that you won't have an error. So you won't have, you will still have something really smooth. And we provide a full error analysis of the number of tetrahedra which you need to do in order to do some animation in the paper. So in summary, you have a compute shader that will animate the tetrahedral cage, tetrahedral mesh. Then the interval shading will compute efficiently all the ray intersection, all the ray tetrahedron intersection. The fragment shader will find in parallel all the contribution of each small segment of ray that intersect the tetrahedron, and we compose everything with the ROP operator. So let's go to some results. Here, all the results are rendered at full HD with the RTX 4080. So here we have some voxel animated. It's voluntarily large for visualization purpose, but you can do it with a really small voxel grid. Just for information, in all the animation that we'll show, we use the same tetrahedral cage that use a 26K tetrahedra, and it's equivalent to a 90K rasterized triangle. So you can animate voxels. You can animate 3D noise. Yeah. And because the representation is defined in the RESPO space, you can do a bit more. You can have some animated dynamic 3D noise. Here the noise is changing by time and still being animated. Globally, you have some 2 levels of animation. You could do the same with voxel, where you edit the voxel in the RESPO space, but still animate it with some real character animation. One thing that was not possible with iteratively curve ray tracing is that we can self-intersect. It's not a problem. I'm not the best animator, I'm sorry. And same, another thing, because we use the rasterizer, we can it's fully compatible with the classical rasterization pipeline. Just use the Z buffer in order to find which is the closest hit for opaque surface. And here, and because it's compatible with the rasterization pipeline, you can use a classical algorithm like here the shadow map. The shadow is projected on the it's a side distance field, and everything the dinosaur is a side distance field, and everything else is just triangle. So it works. And but one thing that we can't do really, it's more complex volumetric things, because we are rendering the tetrahedra in unordered fashion with the rasterizer. We found all the piecewise intersection of array with the tetrahedra in the same time. With the rope operator, we blend it in another way. So we can't do semi-transparent volumic data, but we can still do some optical depth transparency or things that doesn't need an order dependency for the rendering. So just a quick recap of the contribution. We propose a rendering pipeline for animated meshless representation in real time that is compatible with traditional scene graph. And the animation workflow to animate them is close to the one artists are used to. You just have to animate a voxel 3D grid, a tetrahedral cage, sorry. But still, there are some more work to do. Our approach is unordered, so semi-transparent volumic is not directly possible. It's not hopeless. We have the same issue that people usually have with transparent things, with triangle. We could sort the fragment into with a buffer or something else, but it's not directly compatible. Ideally, in the professional workflow, we will adapt the discretization of the cage based on the animation. Here we just use a high number of tetrahedra, but you can adapt it in order to have more tetrahedron where the deformation is really small, where there is high frequency deformation. Unfortunately, and one thing that is one problem with our method, that it's not really a problem, but the deformation is implicit. We never actually deform the object. So if you want to test some collision with the deformed geometry, it might be difficult. We have some more work. And finally, I didn't find really a UI to create an animated tetrahedral cage. That's why we used first a shell and then tetrahedral interior. So there is some work some UI work in order to be able to work with volume. And yeah, thank you. If you have any questions.
All right, thanks, Pekon. Any questions?
Nice stuff. I'll grab one. And I think maybe I know the answer, but to double check. The way that you're rasterizing the tetrahedra is still compatible with the early depth test, right? Because they're conservative in the right way, I imagine.
Yes and no. When you rasterize the tetrahedron, if it's you know that all the tetrahedron is behind an object that you can only call it, but you are not sure to find an intersection of in each tetrahedron. But and one thing that may be not clear, when we found an intersection for the surface, it's this Z that we will use for that we put in the Z buffer. But yeah, you can do some early calling. Each tetrahedron is rendered separately. You can do some first-round calling also. There's no problem.
I think this is very nice work. I'm curious, have you experimented with neural SDFs, like SDFs parameterized on a grid? And will that be compatible with this animation approach?
With what? Sorry, I'm sorry.
Sorry, neural SDF representations?
No, we didn't try with it, but it should work. The only constraint that we can, because we just deform the space around the geometry, it doesn't really matter what is the base algorithm to render the geometry. It can be a neural or something else.
And will it be possible to propagate gradients, you think, back to the deformation parameters in your approach, or do you see any issues with that? Because I'm envisioning using this in an optimization pipeline, maybe to sort of deduct the animation parameters from images. Or?
I really don't know.
Yeah.
I'm sorry.
We can discuss it offline.
We can discuss it later.
Right. Any other questions from the audience? Right. Let's thank the speaker again.
Welcome to today's keynote. I'd like to introduce our keynote speaker, Angelo Pesce. Angelo is a seasoned real-time rendering veteran and has held engineering positions, senior engineering positions at major game studios, including Electronic Arts and Activision Blizzard. He has contributed to quite a few AAA titles, in particular the very popular Call of Duty series. In his current position at Roblox, Angelo is a senior technical director and oversees the engine architecture. He co-authored the latest edition of the book, Real-Time Rendering, and co-founded the Rendering Engine Architecture Conference. Today, Angelo will take us on a journey into the future of real-time rendering. Please welcome to the stage Angelo Pesce.
Let's do that. Thank you. All right, let's get this done. So, thank you for the awesome introduction that allows me to skip this and go straight into the meat of the problem. Specifically of my problem here, which is how I can compete with them. Look at them, they're smart, they're handsome, they're accomplished. Well, if I can't beat them, at least I thought I can put my Italian hat on and be louder. And this is how this talk came to be. It will be a little bit different for HPG, but also for myself. I have not a single equation in it, which is probably my first time. And here is the plan. I thought it would be useful as someone from the industry coming to an academic venue to talk about our problems. But I also wanted to make it fun, not come to tell you the usual, that transparency is hard and GI is not solved and all those things. Moreover, I've already done that in the past, probably too many times. You realize that you're old when you see that your slides are in 4/3. So instead, let's add a twist. Let's try to predict the future. It sounds fun, and it has much more potential for my embarrassment, hopefully only in retrospective and not like straight today. The talk subtitle, if I had space for one, would be how to navigate the future without hype or hate. And this is how we're going to do it. First, a good theory needs to state its assumptions, and I think even a bad one should. And then from those assumptions, we'll try to derive more or less logical conclusion in the form of bold bets. And let's right into part one, the industry. First of all, the industry, what industry, right? Everything trends towards real-time, and real-time rendering is everywhere. Web, commerce, AR, XR, digital twins, like the industrial application side, real-time CGI, VFX, the stray short there, it's pretty amazing to witness. We live in exciting times. But here, I'll still be talking about video games for a couple of reasons. I think it's still one of the largest consumers of real-time rendering technology. It is an industry currently facing some transitions that are interesting to investigate, and it happens to be what I know best. This first part is effectively an abridged and updated version of a previous talk I gave, the value of pixels. And it starts with my "you won't be Carmack" hypothesis, which goes as this. In the early pioneering days of game dev, technology directly unblocked new possibilities. Carmack takes BSPs and creates not just a game, but one of the biggest genres in the industry even today. Hardware and software innovation pushed the whole industry forward. Then we moved to a stage that I call competition for excellence. So here, better technology became a back-of-the-box feature, being able to render at certain frame rates, resolutions, or in general, certain rendering feats were a competitive advantage for a product. Better technology meant better sell, both on hardware, software, console walls, all that jazz. As time went on, we also saw another kind of expansions, games going beyond the box with the rise of social gaming. In the photos here, I actually chronicled the evolution of social feature as I personally experienced them from a first-person view. So those are a few of the game I was lucky to help on. From my very first shipped title to my current position. And I went basically from single-player box titles to online, DLC, microtransactions, season passes, and now with Roblox, of course, my company is one of UGC content creation. And today, if you observe, I think like all AAA franchises are platforms. Fortnite, Creative, Roblox, of course, UGC stuff, but even in non-UGC games, if you see the launcher of Call of Duty, or if you experience FIFA, and its community around it, like the streamers, everything, game engines are really containers through which we push a ton of content in the service of a community. The box really doesn't exist anymore. It's the continuous content delivery that is what sells a given platform. And let's go to the extrapolation phase, right? Like, what are the consequences of this? So extrapolating, we can imagine that for games as platforms to keep expanding their content reach, they'll want to be able to deliver content everywhere. And actually, this is already happening. I did not know of this Xbox GDC poster I put there in the corner when I started drafting the presentation. But then when I started looking for images, like this is describing exactly what the point that I wanted to make. So what does this mean for any of us? I think rendering, at least intended in the traditional way of better graphics, is less of a direct driver of dollars. Which is not to say that we solved rendering, or that we don't have lots of improvements to make. I said this a few different times now in various venues, so I'm tempted to call this Angelo's test, which works like this. Look outside the window, look at your monitor. If you can still know which is which, we haven't solved rendering. But the point is that realism now is readily achievable. And you can see here even relatively smaller teams being able to pull off quite amazing results. So what are our next hard problems? I think monsters will lie in the end-to-end content pipeline, from creation to delivery and representation to rendering on whatever screen we are going to target. On the creation front, costs are starting to matter. And the industry knew this was coming for a long while. The graph I copied from Ralph Koster down there is from 2018. But we did not invest much in efficiency, at least from the point of view of technology. And content representation is becoming important as well. Yeah, games are too big. We can't keep asking to download 100 gigabyte patches. If we want gaming everywhere, PC, mobile, TV, fridges, whatever, we have to find ways to deliver or stream content with a bigger degree of flexibility. Game engines today are already often more about what goes on in the cloud than on device. Games needs the cloud, and most AAA games have significant back-end infrastructure investments. And here a quick note about UGC. I was not going to talk about Roblox at all, but I think like I can just spare one slide. UGC may seem disconnected from AAA gaming, but I think it's really the culmination of this rise of social trend that we are looking at today. So self-expression is a very human need, not something specific to gaming, of course. And in gaming, this has been manifested since the early days, like if you think about modding or all kinds of experiences that are not designed at all for communication and how people manage to create a community and ways to interact. The real difference between UGC and non-UGC games is whenever this need for creation can be expressed within the game or outside of it. But creativity, one way or the other, finds its way. And of course, in UGC land, with stuff like Roblox, Minecraft, Fortnite Creative, content creation and delivery are directly part of the user-facing products. Right? So those are kind of on the forefront of those problems. And here we reached, I think, a first key point I want to make in the presentation. We do know how to do renderings most of the times, but sometimes we can't afford it to do it as well as we'd like. And with this, I mean that real-time rendering very often is bottlenecked by economics. You can achieve great visual quality if your content is great, even when your math is not the shiniest. But on the vice versa, if you have the best rendering in the world, but the content didn't have the time to mature, you won't get to a final great image on your screen. And I chose here, like, The Last of Us Part 2, which is one of my favorite games. This has what I call almost an unethical amount of sheer content polish, attention to detail that manifests in this amazing presentation. It looks really amazing because of it, but how much human effort did it take to craft? And would that be sustainable for most companies, for most titles to deliver? All right. With that, we get to the more meaty part, which is my bets and also the slightly more rambling part of the presentation. First, let's try to get this out of the way. Otherwise, like, I can just go off stage and close it here. Is human-crafted real-time rendering still relevant? In a way, this is the biggest bet, and certainly the one that is most talked about today. And the pace of machine learning evolution is not a joke. We can't simply dismiss real-time interactive Gen AI because the results today are less than stellar. And it would be really ironic for us to dismiss the effects of the race of computing power. Real-time rendering is the industry where Moore's law has been literally the most visible. If I can be allowed to be an old man for a second, how crazy it is that I actually played both of those games. Like, I remember playing those. In many cases, we are still today putting into action rendering ideas developed in the 60s, now possible due to the increase in computing power. So, the AI world model argument, I find it interesting, so we should at least entertain it. It goes like this, to my understanding. If we wanted to simulate ever-increasing details, lighting, physics, object modeling, at a given point we arrive at grain of sands, and we face the reality of a computational irreducible universe. So we need approximations. And what is great at approximating complex functions? ML and DNNs. Now, if you couple this with what is called the bitter lesson, which shortly is the hypothesis according to which trying to mix ML with crafted models is not fruitful, and one should instead double down on computation, bigger models and more data. Well, if you couple those two things together, the need for approximation and this idea that the best way to do that being a purely learning, purely computational approach, you arrive at what is the possible winning scenario of world models, where having AI going from inputs to final pixel of a simulation engine would be the best strategy. Moreover, we know already that ML wins today sometimes. It can be faster and better than traditional solutions for certain problems. I put them fluid dynamics and actor reenactment. So why would a big end-to-end model not be better at everything? Well, I would posit that real-time rendering is a different beast. In real-time rendering, we don't care just to minimize an error metric. We work on the Pareto front of the best possible solution given energy and wall clock time kind of constraints. In other words, real-time rendering is about pixels per watt. Even simply the idea of rendering somewhere and transmitting the results to video may already be too energy inefficient to being a practical, scalable solution for real-time rendering. And we know that generative ML so far is not great at energy efficiency, even for image generation. So today, I don't really see a fundamental reason to bet that ML will be more efficient at modeling phenomena for which we have efficient solutions today. And it may be even true that if we wanted to simulate grain of sands, machine learning would be the best, even for real time. I would say that it's even probable, but we might never need in practice that complexity. The intercept may be impractically far along the problem scale axis. And I think that this also implies that we should really think about the Moore's law and its purposed death, because that could be a risk for the future of ML or real-time ML. And lastly, even if we were to assume that learning always wins, this does not necessarily mean that it can win by restricting itself to neural networks. Now, neural networks are fantastic primitives. They're flexible, they're trainable, and they're incredibly efficient in hardware. They're basically little DSPs that hardware people know and love. But to compete with real-time simulation, we may need to go way beyond pruning and quantization. We may need to learn code or something close to it. And we already saw this in shaders, by the way. Because at the beginning, GPUs were very simple kind of dot product machines. And then we realized that if we could add more degrees of freedom, more expressiveness to them, even if it costs something in the ability to do them very efficiently in hardware, but that extra expressiveness overall couples to give us more efficient solution to problems if we needed to express them only in that very limited framework. All that said, at the same time, I think it's true that real-time solutions to the rendering equations, how we compute light and stuff like that, are bordering insanity. A pixel goes on screen through a complex pipeline with approximations and assumptions all along. If you have seen a production real-time renderer, it's crazy. Analytical light sources, baked radiance, environment lighting, often in different representation for diffuse and specular signals and stuff like that, having then to integrate with materials and the sources of occlusions. Everything has its own approximations, and many signals then get combined together to reconstruct better ones. And there are like chains of fallbacks. Some approximations are baked in tables and polynomials. Some equations are derived with simplifying assumptions. Sometimes we use, let's say, heuristics, where there is bits of code that you look and you don't know where they came from, but they look decent. And at best, all those pieces of the real-time solutions were optimized in isolation, never end-to-end. Often, we also have multiple paths for multi-platform scalability. If you want to try to find the optimal rendering settings on PC for a given machine, it's really like moving a lot of sliders. And today, these things are really so complex that it would take an entire presentation just to go into the details of the state-of-the-art solution for one aspect of the real-time solution. I actually, for a brief moment, wanted to like chart one thing, and then I realized, this will take me way too long to explain, so I cut it down. It's crazy. So I bet there is still lots of potential for improvement there, especially looking at the accumulated error in the chains of approximations we employ. I do think, though, that fixing those issues now has a relatively low return on investment, especially from an art perspective. And art is what motivated this journey to begin with. Like, it's not that we started to do PBR because we want physically accurate things. Like, we are not in the business of predictive rendering. We're not like that kind of engineers. We did it because it was better for the end result from a perceptual and an art production standpoint. So we have lots of pieces, often done with meticulous science, badly glued together, but in the end, the pixels look good. Even when compared to ground truth solutions, we can get quite close. I think like there are remaining wins, but in fixing our maths are more likely to be in the realm of runtime efficiency than perceived quality. And I bet if we wanted to take those improvements and make them, a good idea is start bringing computers into the equation, because this is way too complicated. There is likely an opportunity for significant progress in our soup of math via computer-aided optimization of all kinds, combinatorial exploration, numerical optimization, program optimization of certain parts of shaders, being able to mix handcrafted approximation with learning methods, and moreover, of course, like being able to minimize error perceptually from ground truth is a very useful tool instead of making assumptions or just eyeballing things. And in all of those bag of tools that we should start employing to simplify our life, of course, one avenue are going to be neural networks. Today, we know that machine learning at the end of our pipeline works, like things like temporal anti-aliasing, super sampling, denoise, and so on. And it's obviously should. Those are computer vision problems where AI dominates. Now, the question is it reasonable to think that this role at the end of the pipeline is the only optimal one for AI? And perhaps it is good to remind ourselves of the property a problem needs to have for DNNs to outperform experts. We know that learning-based methods are good if we have a big space where there is a small surface, a manifold of goods where the good solution lie. And this good solution subspace is hard to model by hand, right? This is critical. So for example, in computer vision, right, the space is gigantic. You have width per height per number of channel dimensional vectors. And most points in this space are random noise. Of course, if I just take one point in this space, it won't be a natural image. Knowing, like expressing by rules, what image look natural and what do not, it's a very complicated task. Like you can just think about something about gradients and edges and textures, you're not going to be very far. So in that realm, learning makes a huge difference. In contrast, if we apply the same kind of rules to the world models I was speaking of before, well, there I think we have problems because it's similar in the sense of we have a huge space, and in that huge space, most of the points are not realistic behaviors that happen in real worlds. Okay, that's true. But it seems to me much harder to try to learn certain things. Like, for example, writing down F equals M times A is much simpler to have something moving than forcing a model to learn Newton's law by watching at videos. Okay, so do we have other good problems of this kind for ML in our rendering pipelines? I think yes. For example, radiance. I believe there is obviously a prior on realistic radiance configuration that could be learned to improve, for example, how we reconstruct radiance from sparse data sources, or how we approximate our rendering integrals and all things like that. Many pieces of rendering pipeline today require heuristics that are beyond what can be efficiently crafted by hand and are much better learned by data. And we haven't explored much to understand what kind of inputs are best fed to machine learning to get the best possible quality per watt. Even just for denoising, which is everywhere, like from shadow maps to AO to the final pixel, screen space reflections, we know that allowing ML to intrude more can yield better results than working on the final human-readable pixel colors. That said, I still don't think that the automation and NNification of the real-time solution of rendering equation will happen fast. That was a mouthful to say. Why is that? Why I don't think that this bet has really big odds? In part, it's because when I look around, I see some reluctance from rendering engineers. Now, I can't pretend to have an objective view of what people are working on, but it seems to me that other innovations saw a more traction, more fast adoption. I'm thinking about stuff like modern GPU APIs, or real-time ray tracing, or SDFs and point-based rendering, right? There are a lot of those things made even for fun by rendering engineers, while it seems that we are a little bit tiptoeing with more carefulness in the machine learning realm. Second, I think that the return on investment, like in dollars, is not high, even with the promise of potentially more runtime efficiency, as it still is something that focuses on the display pixel on screen part of the problem. And lastly, the costs are high, both literally for training and data acquisition, but also in terms of friction. Machine learning is not well integrated in real-time rendering, or at least in the real-time rendering tooling that most video game rendering engineers use. That's why we see, I think, most of the solutions using enhanced from rendering coming from hardware vendors, and why in turn, those by their nature cannot be deeply integrated into bespoke rendering engines. And in that case, it makes much more sense that we see them at the end of the pipeline where you create a library and it's very easy to integrate. Okay, so where could we see more investment instead? And here, I'm going to bet, I'm going to make a bet that goes against some seriously smart people who said the exact opposite recently. Peter, just here last year, and Michael Vance, who presented with me in 2011 at React, and even then he disagreed with me. Now, of course, they are right. Baking is great, certainly can't be beaten for quality per watt or time, as you're baking computation ahead of time. So by very definition, it's there to provide you with efficiency. The problem that I have with this idea that baking is going to be there forever is that it's very inefficient in all the other content-wise dimensions. It's a lot of data, which means more storage, more bandwidth, typically slower iteration, more investment in the coding and the tooling. It's generally less scalable. So yes, it's the most efficient way of rendering, but if we believe that content is going to dominate, this is also like where potential bottleneck may lie. What I do think it's here to stay is temporal amortization. This is simply too good of an opportunity. We know that frames will always have temporal coherence in an animation. And notoriously now, sometimes we do push screen space amortization too fast. That can happen for a number of reasons. One, I think, could be a misallocation in certain cases of computational resources, like where we spend time calculating effects that end up causing perceptually objectionable artifacts because we have to denoise them, and perhaps those artifacts lower the perceived image quality more than what those computed effects are adding. This does not invalidate the idea, though. Like finding the optimal balance is part of the artistry of real-time rendering. And for amortization beyond the screen space, we need data structures, and there is a lot of room for improvement here. We still have not found a great way to represent our signal, like radiance and stuff like that, even in static bakes. And in real time, if we wanted to do this as a caching method with incremental updates, things would be much harder. This is another realm where machine learning could help. And we have now in all dimensions more than we can fit. More than we can fit in memory. Of course, we do auto-core rendering or hard drives, network streaming. Everything is bigger than we can have in a frame. Engines today are effectively orchestrators of data residency, job scheduling, and computational resource allocation, dynamically adapting frame to frame. Which brings us to the next bet. Rendering will extend to the cloud. Now, video streaming is useful in certain conditions, but as I kind of already mentioned, moving all the compute server side is expensive, and the bandwidth is expensive. So streaming unique per frame, per client data, I don't believe is in general the best avenue. And in AAA today, network-based streaming is already a thing. For texture data, for example, largely driven by the fact that our games are becoming so big that storage space is a constraint. Like, people don't have big enough hard drives. Roblox, of course, is an example where everything streams, from the objects to vertices. You join an experience and you don't have anything up front, so it's all network-based. We will need more efficient format for scene representation because of this. Geometry, texture, LOD, compression, procedural generation, of course, which you can see as a form of compression. And once you have that system to stream all the static war data, well, then it's not a stretch to think that you can stream dynamic computation as well. In fact, if you think about it, game servers on the cloud are already streaming dynamic computation in the form of gameplay state. So why not stream stuff that can help rendering? So we should look at the computation that on the server side we can amortize over the world. We have many users in the same simulated world, and world and object space computation obviously can be reused. I'm thinking cloud-assisted rendering in terms of ad hoc or just-in-time computation, things like GI, things like LODs, imposters, visibility, occlusion hints. There are lots of opportunities there. And if we wanted to go far along this reasoning, with cloud compute, temporal amortization, new data structures, then should we rethink our rendering pipeline entirely? Taken to the extreme, what really is optimal to compute server side? Can we create some kind of semi-finished rendering in a multi-view scenario? And then what is optimal to deliver? Can we take this semi-finished rendering data and use client GPUs to do the final assembly to the screen pixels? All right, we arrived at my last topic for today. So far, we have talked about rendering, machine learning, a bit about data streaming. And you probably know what's coming next. Generative AI. And I understand this is a controversial topic. I won't talk here about the ethics of Gen AI training and use. You can ask me later. My opinions were too big for the margin of this slide. This is what I wrote down. Here, I want to try to understand it from a technical perspective, from the product opportunity and workflow angles. Progress is happening fast. On quality, I wouldn't bet against the fact that we'll have 3D Gen with perfect topology, rigging, everything that you need. I think it's nearsighted to think that 3D Gen won't be good enough for production. The real question for me is, will it become something like the next photogrammetry? Real-world scanning is ubiquitous now. It worked, it kind of revolutionized game content production, of course, really for realistic games, not just because it's fast and it can produce high-quality outputs, but because it's controllable. It can be art-directed, it can be iterated on many times faster than traditional modeling. Like some of the artists were telling me, it's much easier for me to take an object and slap some plasticine and model it and give it back to scanning than having to go back and forth with traditional modeling. Moreover, it speaks the same language as our established tools and pipelines. In the end, it creates textures and meshes and objects that we can put in our database and mix and match with whatever else we want, right? And I think those are really the characteristics of any good tool. For example, I believe that those are the reasons why AI code assist works so well. Maybe this is already a controversial thing because some people say, no, it doesn't really work for me, but maybe you're being a little bit ungenerous in the expectations. I do think that it works well, especially the code assist in the sense of the IntelliSense kind of replacement, like suggestion search or coding. And I think it works well because it checks all those boxes. So it is fast and it is high quality. At worst, to me, it's like more or less gives the results of conventional intelligence. And at best, I have to take a step back and say, how did you know that I wanted to write that line of code? Like you have to tell me because you're reading my mind. It is controllable, of course, right? Like I'm just typing, I can accept or not accept. It's completely within my normal workflows, it's integrated in the IDs that I use, right? And I also believe that this is why, at least to me, the IntelliSense mode is so much better than the wholesale text prompting, because that doesn't have this characteristic, right? Like, if I generate an entire program and then I keep iterating through text prompts, it takes me a long time to persuade the model to generate what I want, right? Of course, today in the IDs you have both, so really it's up to you. Now, if you look at the same thing, Gen AI for 2D and 3D art, on the other hand, the situation is the polar opposite. So we coders are getting it the best. If you have a look, okay, quality, as I mentioned, I don't think it's the real issues. It's already kind of decent, and I believe it will be better, it will be solved. But iteration speed is absolutely terrible. The controllability is terrible. Like, it's not fun to have to know how to express what I want in text prompts that the machine will like. Like, this entire field of prompt engineering is a big warning sign that this is perhaps not the right way of interacting with those models. And in the end, you don't even get discrete, isolated logical objects that I can understand. Like, I can generate something, and then I have to regenerate. Okay, I know that there are models where you can take subsections or whatever, but it's not creating the kind of elements that are compatible with the regular pipelines we all know and love. So this is my bet. for generative AI to really thrive, at least as part of AAA content production, somebody has to figure out what it means to have an AI art assistant or AI art assistants in general. Otherwise, I think this will work, but perhaps not in the context of traditional AAA gaming. That will create in some other genres. Text-based conditioning is not going to cut it. It has to be interactive and real time, and people have to deeply understand artist workflows and needs. All right, and we are reaching the ending. Let's see. So my thesis here is that we defeated the first boss of real-time rendering. We know how to make pretty pictures fast. Pixel quality search 2010. And yes, real-time rendering is not solved. It's definitely a mess. There are lots of opportunities to do better on all axes. But still, it's good enough quality, and it's largely achievable by everyone, that it's less of a differentiator. It's not driving sales like it's used to. And more often than not, when we don't reach quality, it's more of a matter of content iteration than it is because of some error in our programming. Our next challenge is then solving the bigger pictures. The bigger picture, delivering quality and quantity everywhere, on every device and on every screen. And it's truly doing all three at the same time that it's hard. Like today, you can have quality and ease of production if you don't care about content being widely available. If you're doing something only on very high-end hardware, your problems are lesser. You can have quantity and wide distribution if you don't care about quality, meaning, for example, extremely stylized art styles. Yeah, of course, like then they are something that if you choose your constraints carefully, they can be delivered everywhere. They cannot take a lot of data or computational resources, but then you're abandoning that kind of like realistic quality that we all know and love. And lastly, you can have quality and wide distribution if you are okay going through the immense pain of the state-of-the-art rendering engines and rendering pipeline of today. Your several thousand people teams making the gigantic blockbuster games. And now, alas, this is why I titled the talks Hallucinations, of course. I do believe that machine learning is here to play a role, but it can play a bigger one if it works most closely, if it more closely aligns within the industry's incentives and costs and way of working. All right. Questions? Thank you. Oh. Sorry, I almost forgot. Let's do this. Ale. Thank you.
Thank you, Angelo, for this presentation. Any questions in the audience? Raise your hand. Other than that, yo, there we go.
So you said you can't be John Carmack, but if you were 22 now and wanted to do a one-person studio leveraging AI somehow, what would you do?
Sorry, maybe the microphone is off. Can you? I didn't really catch it.
Which button? No, it's on. It's on? Is it on?
Yeah,
I just wasn't holding it close enough. Suppose you were 22 years old and want to be the next John Carmack, but with AI instead of BSB trees. What would you do now to do a one-person game company in the next couple of years, so not long-term? Assume the bad tools.
So I don't know exactly where you're pointing at, right? Because kind of like not John Carmack, what I mean there is like your code, your rendering prowess changes the entire industry. And I don't know if like, I mean, yeah, it may be true that the AI kind of like opens a new thing there. Maybe that is too much of a bold bet for me to make, but that's a very interesting point, yes.
Great talk.
Thank you.
I've been thinking about this for a while as well, and the bitter lesson says that like general methods will beat expert-made models given enough compute. And I've been wondering, like, we don't have enough compute for everything yet, but what are the areas where you think we do have enough compute and we can build general methods to replace expert-built models, like microfacet models, et cetera, et cetera?
Yes. So then again, I want to be clear here, and also, I will publish those slides. I have like 1 million more, but I was too stressed that my talk would be too long, so I culled most of them. So perhaps that also will help. But basically, my thesis here is that real-time rendering is not even about, okay, eventually you will have enough compute power. It will always be about what is the most efficient way to do the same thing. And that drive of efficiency is actually what drives most of what I've seen. Like even when I talk, hey, our rendering, math, and pipelines are extremely complicated. A while ago, I was saying, I don't believe, for example, that real-time ray tracing will make real-time rendering easier. And my main reason was real-time rendering engineers will take ray tracing and use it in one more step. It will add. And the reason why it will add and not replace is that if I can solve half of the frame very efficiently, right? And it takes a lot of code, and then only this other part needs ray tracing to go the extra mile, I will always take that. That complexity is the chase of how many months of a programmer you want to spend to get 0.1 milliseconds back in your rendering pipeline. And it has always been, yeah, we will, especially at the top end of the state of the art, we will do whatever. If we have to double the code side to get like 20% improvements in the frame time, we will do it. That is fundamentally where the complexity comes from, right? And couple of that, sorry, this is a long answer, but I also do believe, and this is one of the slides that I didn't put here, of course our computation power is still going to rise, but if you also look at the devices in the hands of people, that's actually not really happening, right? Like the top end, you know, your iPhones and whatnot, they're still growing exponentially, but there are so many more people buying cheaper devices for which the efficiency in watts is paramount. And we are, if you look at the industry, doubling down on the low end, like trying to scale down instead of chasing the high end. You can see how many AAA games now port to PC and try to go more low end on PC, or how many AAA games want to port on mobile. There is much more compute there that we want to exploit than focusing like we used to do traditionally on the very, very, very top 1%.
Which type of game developer do you expect to benefit more from Gen AI? The small indie developer or the big company with lots of resources to throw at it?
I imagine the small indie dev right now. And the reason why is that, then again, big bets, don't quote me, it will be completely wrong, right? But what I'm seeing is that the companies behind Gen AI, of course, want to target the largest number of users, obviously. And it's so much better to try to make things for an emergent new market than trying to focus on, you know, the 10 gigantic gaming studios with our tendency of, you know, consolidating those in bigger and bigger and bigger gaming studios. So I don't think there is enough market there to be interesting. And I kind of saw it even other times. So like when we had YouTube, right, we created a new way of creating movies or video-based content with huge professionality, but that didn't change the way of Hollywood movie making, almost at all. It just created this new, gigantic, and much bigger segment. So right now, I think that is the answer. If someone tries to like solve Gen AI specifically for AAA, as I kind of was hinting, then there is a chance that both will benefit.
So, especially in the context of AAA gaming, it seems tempting for studios to replace professional artists with a Gen AI approach. But if I understand you correctly, that's not what you think is likely to happen. If I understand you correctly, it's more like this IntelliSense type of assistance.
Now you want really to like go into controversial stuff. So, okay, then again, my personal opinions here, right? I believe that that is not mainly driven by technology. Like, we saw it always. It's not that Gen AI is, okay, now we have Gen AI, the crisis of the industry or anything. Like, when we went from keyframed animation to motion capture, when we went from 3D modeling to photogrammetry, as I was showing, we had a lot of technologies that draw the artistry in game making to higher and higher level, right? Like, then again, motion capture, now I need an animation director for actors or for athletes, less than the most experienced keyframe maker, right? But we didn't lose people in the industry at all. And I think so that the main driver of we need more or fewer people is not so much the technologies, but the economic realities. So of course, if that market is not expanding exponentially as it was before, then you live through tougher times. But okay, I'm not an economist as well. There are people who can speak much more eloquently on this, but this is my opinion.
Any more questions?
As we approach photorealism with generative AI, I think something that's lost is the disparity that we still have from reality. It triggers simulator sickness in people, and I think that people who are growing up today's society who are exposed to Gen AI from a starting point are probably less acceptable to that. I don't know if that's true, but do you have any comments with regards to that? Yeah, it's hard to describe it further than that, but I can go into more detail if you'd like.
Sorry, can you repeat that? I didn't catch it. Also, if you can be a little bit closer.
So, like, if you talk about VR, right, and there's a huge problem in VR because of the disparities from reality. Like, we have the visual acuity, proprioception, and the stimulation, right? And when things are not aligned properly, it causes sickness in us. With Gen AI, like, I can't go online and watch AI videos because they generate simulator sickness in me because of the disparity from reality. It's going to be something like the eye movement, for example.
I see.
You know, and that is really like I don't know if like children are going to be is kind of controversial. Children are become desensitized to that if that's the reality. But like for me, a clean path trace render, it just triggers everything in me that's like creates this contentness that I want from video games. And I think that does not happen with generated AI content for me individually.
Yeah. No, okay, I get it. So it's a very interesting observation. To be honest, I don't consume enough Gen AI content to like have experienced that. I think if I can be, because I don't have an answer for that. It's too far from my expertise. I think a little bit, the only thing that it's closest to that I was talking about is how sometimes I think we risk, and we always did, to be honest. It's not like a new thing that, oh, now because of denoising and whatever, there are those problems. But it's very tricky to optimize for perception. So sometimes you do unchase things that then have different kind of artifacts, right, that maybe are good in static images or when it's converged or at given power levels, and maybe they weren't the optimal solution, but that has always been a problem, like that kind of thing. And we even saw today, and like how have always been very passionate about perception in computer graphics, and it's still very, very far from a solved problem. So I think there is a little bit still to improve about that.
Thanks. That was an amazing talk. One of your big bold bets was much more cloud gaming. And it's actually heartwarming to hear, because I think in the last year or two of AI everywhere, everyone's kind of ignored the big change that's happening. Do you think does this mean that every AAA title in the future is for the most part on most consumers' devices going to be streamed from cloud in one way, shape, or form? Or do you think it's still going to be very stratified, where certain titles, like the Robloxes of the world, are going to be doing more cloud gaming, but you're also going to have a lot of other kind of conventional single-player games or small-scale indie games that are still not cloud.
Yes. So, my opinion, I kind of hinted at it, right? Like, I think that you are more likely to see a lot of more complicated data being streamed from UGC people, just because there is a greater need, right? When I said, of course, when you do UGC stuff, this content representation, delivery, creation experience is really part of your product, of the things that people touch. That is the reason that I think probably you will see it there first. For bigger AAA games, see what happened, right? Like, there is a lot of titles are streaming textures because of the concrete need of you don't have hard drive space. If they don't have any other thing, like in the end, you only solve the problem that you strictly need to solve, right? Like, so there are certain things, certain products where those problems are more in your face, and certain where, well, maybe I should prioritize other things.
Do you have a question? Yeah.
Hi, yeah, I think this was a really interesting talk. This might be a bit of a philosophical question, but I was thinking, like, one of the concerns with generative AI is the fact that, you know, it's trained on sort of the state of the world, right? So it reproduces biases, it reproduces sort of like the predominant styles, etc. Is there a concern that the integration of generative AI into art pipelines, even if it is done in an ethical way with respect to the artists, is there a concern that that could stifle artistic creativity?
Oh, well, all questions that ask really to stretch me way into the future. Yeah, I would, okay. Because in the spirit of taking wild bets, my wild bet is no. And the reason why my wild bet is no is that I believe even stretching to, you know, very fantasy scenarios and everything, there is sort of a prior or manifold of reality, right? Like even throughout art history, throughout all kinds of styles, and probably that derives from humans, right? Like even, okay, see the evolution of music and what kind of tonalities and compositions with people all over the world arrived at, right? There is clearly something that it's more appealing for humans in general, and there is kind of the hope that you will be able to learn some of that in this gigantic space of random stuff where most of it is complete noise that makes no sense and it would never be pleasing. That said, then again, it's a very, very wild bet. I don't know. Yeah.
All right, I believe we're out of questions. Let's thank Angelo again. Thank you.
Thank you. Oh, and as I mentioned, I will at a given point publish this, and it has a ton more slides because that is a way for me to offload my anxiety. Like I want to say too many things, and that's like, okay, I'll put it in slides. So if you enjoyed this, download the slides when I publish them. Thank you.
We'll have a few more comments from our local chair, Jeppe, and I think maybe also Christian.
All right.